this probability, I think. But Jupiter just
You know, he made me get a hot drink. I'm getting iced tea.
The fish is the whole.
Somebody needs to build it.
That's
rice.
That's a seaweed. You should try it. That's my favorite. Maybe you like.
Sorry?
Sorry.
Yeah, you can get started. Yeah, don't worry.
Okay. All right. I'm gonna start this with like some background stuff. That way people can kind of like crawl in when they get here. So I'm Andy. I work at Johns Hopkins Applied Physics Lab. And I guess. I do a lot of control stuff, so that's what we're going to be talking about today. Michael's also going to be talking a little bit this afternoon, so I'm going to kind of set the stage on just methods for optimization, what control looks like, and why it matters for quantum, and then Michael will kind of like help guide you guys through, I guess, the theory of the field, where it started in quantum, and we'll kind of connect back to like how other fields do it, like robotics, aerospace, and stuff. So yeah, that's kind of the cell is basically you have, unitaries and state preparations that you want to design on your hardware. All of that really matters for, accurately operating it for whatever you're trying to deliver, whether that's, sensing or whether that's computation and error correction. But ultimately, you're just looking for like how to wield the model that you have of your system to do all the cool stuff you want it to do as accurately as possible, which is something pretty ubiquitous throughout like a lot of engineering. And like Michael's going to hit this, I'm just like walking through these slides because I want to give people cushion. There's a long history of quantum optimal control. What I'm going to try to get you guys to in my talk is like, there's a lot of structure to this problem that you also want to bring to task. So like we're talking, constraints, things that you have to worry about because, a qubit isn't a perfect qubit. There's a lot of other like energy levels floating around in the system. And like, there's a lot of other systems that you're trying not to address at the same time as you're controlling whatever you're focused on. And you have a lot of errors that you kind of want to deal with. And so there's methods to kind of tackle these challenges. And of course, like huge space also that you got to kind of like walk around. And I mean, ultimately, like quantum, it turns out, has a pretty nice structure that makes these problems easy until you start to factor in all these constraints and then you kind of like wreck your risks a little bit. And then you have to kind of be a little more careful. So what I want you guys to kind of get and what we'll cover in this is like classical control, basically anything with an inertia, like any Lagrangian you write down, it's going to have a differential equation which looks something like this. Got a drift part for your state. And then you've got a control affine part. That means that like the control shows up linearly over there, hanging out here with some other kind of dynamics. And that's how you kind of capture things like both Newton's laws, but also like rotations, like the satellite docking problem, for example. And when we switch to quantum, it looks really close to that. So basically like it's similarly to this like docking problem. It's like a lot of rotations. It's just that now you have rotations and like a massive, massive space. All right, so that's kind of the game is like, how do you wield all these various rotations to kind of deliver what you're trying to deliver with all the complexity that might entail. But something kind of working here is like, to our advantage, this is not that bad because you saw that like on the other side, it's functions. And in fact, like those functions are kind of like linearized away because of the fact that quantum is itself, acting on, you can think like a function space, or it's acting on kind of all these kets, so it's linearized. So this is bilinear instead of just linear, so you kind of have a little less mess, but you trade for that with like, it's still nonlinear, so we're going to need all of those methods. So again, we'll talk about how to deal with that. And like ultimately the like lens, what's up?
Yeah, sorry, quick question. What is U of t over there?
Oh, that'd be like a unitary matrix. So this is like just Schrodinger's equation. So it'd be like Schrodinger acting on the propagator. You could think like if you just put a ket in front of all those u's, that's Schrodinger's equation.
Okay.
And you just shoved it onto the operator
Yeah.
instead of acting on the state. So just kind of flipping the picture. Yeah.
And J's are the sources, different sources, or
J's are different controls. That's a good point. Yeah. So like what I'm thinking here is like your ability, we'll talk about this, I guess, but like your ability to like rotate about certain axes. So think like I'm driving to either like excite my system from like the 0 state to the 1 state by resonantly driving. So it's like a rotation between the 0 and the 1 to resonantly drive that like flopping, that swap. Or it's an exchange coupling where maybe you're like swapping an exchange from one mode to another. And so you have a lot of different sort of, for example, in superconducting, you're like engineering circuit elements to have these operations. And then you like drive these circuit elements to deliver whatever thing you're trying to do. But on like other systems, they kind of just come with the territory, right? You like put two atoms close together and then like you excite to like certain levels and then you get like some sort of Rydberg interaction or something like this. So you have, or you like put two ions in a chain and then you wiggle them around and they get a sloshing and you've got these like shared motional modes. So it's all about kind of like engineering the physical system, but at the end of the day, it turns into like a matrix with entries that allow you to rotate about a different axis. Okay. And that's really like, you know, this is the punchline, and then we're gonna walk way back. So like, yeah, we'll definitely get to all this stuff and talk about how to do it. But like, I guess the point is, I want to hit all of the concerns of like, how do you deal with all of this stuff, you know, while you're driving the car and doing reckless stuff? Like, how do you make sure that you stay in the lane, don't run out of fuel, don't kill the driver, etc. So I think since we've got most people, we can maybe jump into some actual discussion. So we're going to need basically to do a few things. We're going to need optimization, and then we're going to need to structure that optimization in order to like actually get the types of control that we're targeting for the quantum systems. So let me switch over to some notebooks. Okay, so I guess
increase the font a little.
yeah, we're gonna make that way bigger for sure. Okay, and I'm also gonna, let's see if I can make this. Is there like a way to full screen notebooks as well? I believe there totally is, to minimize some of these bars. Okay, that's something. See if that helps at all or makes it worse. All right, how do people feel about that? Pretty good?
Mhm.
Cool. All right. Okay, so I guess main takeaways from this section, I just want to introduce optimization because that's like the first piece we're going to need. And so like we're literally going to just like walk through gradient descent and Newton's method and how to add constraints for like just 1D problems and 2D problems. The main thing that we're going to do here, and this should hopefully take like the first kind of like section of talk, like 40 minutes or so. We're just trying to get to the point where like, hey, we have this problem. It was minimized or like solved for a good operation to do something subject to a bunch of constraints. So I want to kind of like make sure that we can all get to the same page of like how to do that. And we're also going to hit like, watch out for like all the weird stuff that could go wrong and how do we avoid that to make problems behave the way that they're supposed to. So cool. Okay. Okay, so I'm gonna get you these. Yeah, what's up?
Could you share these notebook?
Yes, but not right now. So I have so the APL is the person who's normally supposed to like let me share things, you know, like standard just like bureaucracy stuff, was on vacation.
Yep.
So we're currently working on that. But right now, you'll just have to kind of hang back and I'll have to click through stuff and you'll have to like wait up. So let me okay. So that's fair. We'll get that. All right. We're gonna use some pretty straightforward stuff to start. I actually don't even think I need forward. I think it's literally just all linear algebra. So that's fun. Step one, minimization. So we're going to start with a cost function, right? And for basically any smooth problem, the sufficient condition for a critical point, right? Like for this function is just that the gradient is 0. That we're all on the same page. Great. The necessary piece also, you also need both of these necessary conditions is that you need the second derivative to be positive definite, and that's because you need it to curve so that's a minimum and not a maximum. So we're going to hit this, so keep this in mind. But gradient descent is basically just a fixed point theorem where you iterate that exact equation, which is just like keep on applying this again and again and again, and then this flow will get you to that exact point. So we're going to set up some simple demos. So yeah, there we go. Okay.
Could
So-
you scroll up just for 1 second?
What's up?
Could you scroll up just for 1 second?
Yeah, absolutely.
Just looking at the gradient descent. Okay.
Yeah, so exactly. So we're going to start at some point. We're going to apply some step in order to move in the direction of the gradient. And we're going to like show what this algorithm does. Basically, every time I present these algorithms, I'm going to then just like show you some pictures. And we're going to like hit this like 3 or 4 times so that we can like see it happen as opposed to just like an equation. And so that's exactly what we'll set up here. So we're going to start with function. It's gradient, which like, I think I did it right. And then second derivative as well. So nothing too fancy here. And I'm going to add 2 functions here that just plot this thing for us because we're going to be iterating this a few times. So all I want is a quick plotting utility so that basically I can mark these again and again. So you'll see this in a second. We're going to take a step. This should look very familiar. It's what we just looked at. And we're just going to play with like the only parameters we have so far. So let's take a peek at this. First, let's just take a look. So we're just going to be looking at a landscape like this. It's quartic. We've got 2 minima. Cool. And what we're going to do is set this up with an initial point and a step. And basically, I just want you to see gradient descent, which is exactly what you'd expect. Go downhill, pretty stable, life's good, you get it. Okay. And eventually, slowly, surely, we'll get there. Okay. Got there. Wasn't great, took a little bit. Let's make that worse. So, okay, so this right here, let's move it down here. Was our step size. What happens if I make this way smaller? Okay, if I make this way smaller, then you would not be surprised to see it's even more miserable. So we might be clicking for a while, but we'll get there. So a few takeaways, super stable, right? Take tiny steps. You've got kind of like nice monotonic convergence. That's cool. But like maybe, you know, on a big problem or something, you don't have like this much compute to just like chill and wait. So you kind of are wondering why you're gonna do this, if this is really the best you can ever do. So you might think, awesome, you know what I'll do? Make it bigger. Because like, duh, like it's going too slow. So we can try that. Let's give that a go. Okay, no, it'll be fine. We'll get there. Okay, off screen. Where did it go? Let's see if we check in on what we just did. What exactly happened? Let's get rid of the limits. Let's just like see what goes down. Okay, we're way off here. That's fine, you know, like we're up here. Maybe we'll recover. Okay. So not great. So clearly we have this like nice regime where this like linear step, very chill. We can just like walk downhill without an issue. We get a little greedy. all of a sudden that linear approximation, all the sort of life's good, just keep walking downhill, blows up for us. So just doing gradient descent and tweaking that like line search might not be the most fun time.
Can we just do like a mix of these like large steps? So in the beginning, you do some large steps, but when the differential, changes as you get closer to the minimum, you recognize you need to take smaller steps and then you just take smaller steps.
Yeah, and in fact, the question would be, how would you know whether, so let's just look at that initial point again. How would you know whether you want to take a big step or a small step? So like if I'm over here versus I'm in here versus I'm over here, how might I know like which times I want to take a big step and which times I want to take a small step?
The second derivative, no, yeah.
Yeah. So we're basically just gonna like try to do something about the curvature because like, okay, great, we captured gradient information. And for large systems, stable. So like you're in a really high dimensional space, you just want to make some progress, gradient descent, right? Like you're training a neural network, gradient descent. But like if you want to do something with like a lot more structure and you really want to exploit what you know about your system, second derivative. Yeah, exactly. Okay, so that's what we're gonna do. We're gonna, instead of approximating the function linearly, we're gonna get a local quadratic approximation to this function. And that means expanding this sucker about delta x. Great, now you have the second derivative and some little delta x's. And what you can do is you can say, well, what would be the minimum of this quadratic? Because that would be like a smart thing to do, right? Like look at it locally as a quadratic, use the curvature and just say like, well, okay, if this was a quadratic, I'll just stop at that bottom point and have that be my minimum. We'll show this in a second. So you solve this linear system, you got this matrix inverse, okay? For us, it's gonna be easy because it's just division, but like keep in mind, this is a matrix acting on a vector, something that like, might come back to bite us at some point and we'll wanna be smart about. So here's our Newton step, like I said, x, and then just backslash for the pseudo inverse. So we're just taking the matrix inverse. And we're gonna also sneak in here that local quadratic approximation because we want to just keep an eye on like, well, that was the assumption we made. What does that look like? We're gonna plot it. So that's what I got here. And then we're gonna do the same thing we just did. And it's gonna be awesome because it's gonna go better, I think. Let's find out. Okay, first thing, already, that's pretty good, right? Like, check that out. So we drew the picture. Local quadratic approximation, we go to the minimum there, right? And then we take our step. And we can keep doing that. Make that approximation, step, make that approximation, step, done. Okay, so already loving the suggestion of like, that was dumb, gradient descent was too slow. Let's get a little more information in the mix. And it's like doing great. Okay. All right. We don't need that anymore. We learned, we see it. So everybody's good on like local quadratic approximation, go to the minimum of the quadratic. Where was that on the curve? That should be great. We're in business. Yeah, what's up?
This point of view, you've got this. But what if you start
Local
from
minimum.
this point?
Yeah, always local, 100%, always local. Yes. So these methods are always local. So if you have multiple minima, there's no guarantee that you're going to pop out from this minimum. So let's do it. Minus 1.5. Let's just go to the other side, right? What's going to happen? We're going to walk downhill toward the other minimum. We're not going to like hop over. We're just going to get stuck there. And that's fine, right? Because like, for the most part, that's the game. We'll talk a bit about how this differs in problem structure and local minima kind of later, but that should hopefully get the right picture. Okay, let's pick a different point just for kicks while we're talking other points. What about like something more interesting, like in the middle? Just to kind of like, keep it spicy, see what else can go down. So let's see where we end up if we start in the middle. Oh, wait, hold on, let me hit enter.
Now you have a decision to make.
Okay. Well, that was a weird choice, right? Like, I don't know. I would have thought to go right, personally. Okay. What happened?
the maximum, because you're solving this quadratic for its
Yeah,
minimum or maximum in
Nice.
the equation.
bingo. Okay, everybody catch that? Let's put the like local Newton back in. So reset this sucker. What's going on here with this local quadratic? Yeah, exactly. The concavity is wrong. So we did exactly what we said we were going to do. It's just that that was not the right answer because we had the wrong concavity of this this Hessian here, or the fact that we had an eigenvalue that was negative in our Hessian. So as we follow this, things break. Any thoughts on what we could do to fix that? Like, how do we make something not negative anymore?
Do you just
Are we-
multiply it by -1?
Well, yeah, we could multiply it by -1. I'll go even simpler because multiplication is fancy.
Mhm.
I'm gonna add numbers. So I'm just gonna like add numbers until it's not bad anymore. Because like, why not, right? Okay. Let's do that. And we're gonna give it a name, regularization. So now we're gonna fix things by saying, oh no, add a number. So check out this. This is fancy. Regularized Newton. If it's negative, make it non-negative. That's our algorithm. Okay, cool.
I have a question.
Yeah, what's up?
So in that quadratic approximation, the concavity was wrong.
Yeah.
Can we not already make sure that we have the right concavity for the quadratic approximation so it doesn't go wrong way?
Yes, 100%. In fact, like this is exactly what this check is. While what you just said, add numbers until it's better. That's exactly what we're gonna do. That's it. Yes. Perfect.
I guess if you're in higher dimensional spaces, if you just multiply by -1, some of the negative become positive, but some of the positive.
Yeah. So if you just flip your eigenvalues, all you've done is like, let's say you had a 1, you were like a saddle, and 1 was negative and 1 was positive, and then you're just like gonna flip, and then it's the other saddle.
Yeah.
And you didn't make anything better. But if you add numbers, you add a bowl around every eigenvalue, and eventually that bowl lifts the sort of, if you think of like, I don't know if I can draw it, but if you think of like a saddle, I think all of these are dry erase, right? This looks very intimidating, but I'm gonna trust that.
Yeah, no, that works.
Okay, good. Yeah, so like if you have your saddle, right, like something like this, if you add sure. Let's just pretend that that was a good drawing. So basically, like, yeah, this is negative, this is positive. Then, like, basically, if you add a bowl around this, you'll end up eventually just kind of lifting up this end, and like the bowl will dominate, right? It'll limit, and it won't notice the saddle anymore. And so that's exactly what we're doing if we add it in all directions. That's a good point. So. Yeah, new algorithm, same as the old algorithm, but with plus. Okay, so other things that are going on here, I'm gonna give you another Newton step function, but we're gonna keep track of the like step we took just so we can see that we've got a new local quadratic approximation, which is a different shape, just to kind of sanity check that we're following the right steps. The other thing I want to make a note of, I think that covers it actually. So same game. Here we go. We got to pick another parameter, right? Now we've got this like regularization amount. So we've got another thing to kind of futz around with, but we'll see how it goes. I guess you can imagine. Okay. So maybe not the best, but let's keep trucking and see what happens. Okay. So not bad. Nice. Okay, so a few things. Notice that we had to add a bunch of stuff here. And then, okay, it went off screen, but that's just because like, we were really close to where that's like basically linear. In fact, like pretty much it was actually 0. Like this eigenvalue was like -2. We had to add things twice. So you get like this really wide bowl to fix it. But like, is it clear that basically you have to go off screen, go to the minimum, and then we just like fall down this hill. So we fixed at least that messy problem where we have the negative eigenvalue, and we're now following a goal. Cool. Okay, so we fixed it. Life's good. Okay, wait, that was my bad example. Hold on. Let's get a better one. Where, hold on, reset. This was supposed to be the good one. Oh yeah, that's so much better. That's what we should have started with. Check that out. Look at that. Basically in 2. So problem solved, all fixed. And then if we change it to that other one, then it's not so good, but it still worked. So that was the first thing, is basically if you pick a bad choice, you still can step really, really far, and that can be risky. We'll talk about. But okay, fine. If you get a good choice, life's good. What about if I am just like, scared again and I pick a really small number or a really big number? Like, sorry, very conservative, and I want to make the bowl huge so that I get rid of that, and I'm just like positive that I've got a nice well-defined local quadratic approximation. What's going to happen here, we think? Well, first, how big is the step going to be?
Really large.
Well, so if I have a very big quadratic approximation, then
Oh, yeah.
You mean like this?
it's
is
a
what you mean by a large bowl.
yeah, exactly. A large bowl means a huge penalty, means a really big, like every time you take a tiny step away from the point, then you're like just stuck with this like massive wall of like the quadratic is just like a little bowl. And so if you regularize your problem aggressively, what does this look like? Okay, other than it's kind of cool looking actually, so I'm gonna keep clicking. That's awesome. But which of our methods?
Did we just got to?
Now we're on a completely different page.
Yeah, okay, so yeah, I hit the line exactly, so I didn't this is why you don't write a while loop, like while not true, just hopefully everything works great, because I definitely hit like exactly the 0 and then hit a line, and so we drew a quadratic, and so we ended up following this line off to like somewhere crazy. So like but which method does this start to look like if you regularize that we've seen so far? Yeah, so we're just like totally back in gradient descent if we over regularize. So basically all the wins we fought hard to get just totally faded away because we were like too scared and we needed to regularize. So takeaways so far, gradient descent, fine, but a little persnickety when it comes to step. So we're like, let's use some curvature information, but then we have to be careful. So we regularize, but now we've just kind of traded one risky parameter for another risky parameter because regularization puts us right back in with gradient descent. Okay. And then the other thing I wanted to hit was basically, we got lucky, I think over here with, oh wait, hold on. Yeah. So where's my here, and then we're here. Remember this? So I think I have a little bit of a, see if we can shift this over. So what I was trying to get at with this, move it to the other side, minus 0.5, move it over there. See what happens. Okay, pretty well behaved actually. It's really hard to break these things. Oh, actually, I forgot. I wrote a different function, so we break it. Okay, so that big step is something that I want to talk about. And what we're going to basically do is we're going to add a line search, which is a way to say, how do you pick a big step that like sort of is the right size? Sort of how do you make sure that you don't overstep? And why you might care. So we got lucky in the other case. Let's talk about, this should have happened earlier so that I didn't spoil the punchline. We're going to come back to that math, and I just want to show you it breaking first. So I have a new surface. Okay. And in this new surface, I'm going to have different points. So now I've got some like local wiggle, but I'm going to do the same game. So this is the same process as before. And what I want to do is just try a few steps. And okay, like for that case, no problem. Life's good. If I were to follow this one and then keep going, I want to see what happens. So here, this was the first step of a search. Okay. Wait, check this out. Don't worry. Don't worry. We'll get there. Okay. Check it out. All right. So that's super lucky. But like, I guarantee you that like playing this crazy pool shot is like not always going to be so kind to you. So what happened here? We took a really big step. And then we took another really big step. And what kept happening is we basically overstepped past the local quadratic approximation. So we were in a bowl, but when we went further, this has a lot of wiggles. So it's like got this local region where the quadratic holds. And if you go way over here, you're in a totally different part of the landscape and a different bowl with different properties. Which means that like you can't just take the giant step that like that quadratic is assuming is valid in like this kind of case. So we got lucky in the other one because when we went off screen all the way to the right, it was just the arm at the end of the curve, no problem. But if there's more wiggles over there in different bowls, things are going to get very chaotic and messy very quickly. So we have to fix that. And the way we're going to fix that is scrolling up to the thing that was supposed to be the punchline of this section and not the start of it, is we're going to add a line search. So there are a few ways to handle like don't go too far. Either you have some condition that says check on how far you went, was it a good choice or a bad choice? Or it's put a trust region or a region around that initial point and just don't let yourself take too far of a step. So trust region is the one going forward. Backtracking is the, like, or line search is the one going the other direction. So we're going to use line searches in this, but I just want to say both words. So this condition, the Armijo condition, is basically saying, how do I know that I've got a good decrease? So the picture is that you had a cost function, which you approximated with a quadratic, but let's just look at the line. And we're just going to weaken that tangent by a little bit. So this sort of like parameter beta, or b, excuse me, is just like a softening of the slope. So we're just going to kind of like be a little more conservative and just say, okay, follow the line, but like you don't have to like go downhill perfectly with the tangent. You can kind of be a little more relaxed. And I'm going to show a picture of this in a second. But the kind of core idea is just like, well, if you went downhill, good. But if you ended up on some other arm or way off in some weird other corner, maybe that was too big of a step. Go back to a region where like the line was reasonable. So I have like no idea how to get back to my menu when I'm in full screen, but I have a picture. Hold on, let's see. Just trying to remember how to pull up the menu from VS Code. Otherwise,
The menu.
yeah, like the sidebar. Is it like that's the bottom one? Hold on. What's the
side one? You can click up in the upper right. Upper right. Do you see there?
Oh, right. It's blocked by my stuff. That's what I want. Yeah. Okay, I wanted to look at this. Okay, so Nocedal and Wright is like a standard textbook in optimization, and this is just a picture of the Armijo condition, kind of from their book. So that's like the classic for all of these methods. And I just wanted to show you like, okay, look, you have some like local linear, you've got a chill region where it's like totally doing what you want, totally doing what you want. And then you have the like bad zone where like this would be like something dumb happened, don't do a line search step and like count this. So like when we were shooting off with this curve, like jumping way up as you like went off to infinity, you'd reject that point because that was like way too big, you increased, and you walk back by just like having and trying again. So like a line search works by like you try here, it doesn't pass the condition, have it, try again, have it, try again. And so you're really, really close to your point. And then you just sort of like, eventually that quadratic approximation is going to be valid. Because like if you zoom in enough, you're good. So that's like what the line search is doing.
So wait, you have it and then, but you're no longer on the surface.
so it would be like, let's say we started with like our quadratic approximation told us we were going to be at this region here, and then this doesn't pass the check because it's above. Then you pick some like arbitrary amount, and then you try again. So that's like a backtracking line search. So you backtrack by having that sort of step. So you just have how far you took in the gradient direction that like Newton's method spit out for you, and you try a little less far. So you know it's the good direction, but you know it's a good direction locally. So you just do a little bit less of it until like the good direction is like in the region it's valid. And you just, if that was no good, you try having it again. And that half is just a hyperparameter, but half is usually the standard. And so this is like the most simple. There are other line searching techniques with different names that people add to sort of make this more stable. But that's the core idea, is you have to just guess and check, basically. Or assign a trust region that's like, how conservative should you be at the start? So either you guess and check, or you be conservative at the start. Those are your kind of two choices. Okay. Get this back in the corner. Where am I? Okay. So, okay, billiard ball nonsense, and then okay. So I forgot that I like totally was out of pocket here with like the order. Sorry. Okay, so here's us. Same exact bad zone as this. I like definitely mixed up what I was trying to like demo first. So here's the scary bad, like no good steps, right? Where you like went way too far. What we're gonna do is we're gonna add that backtracking step. And what that's gonna do is it's gonna make sure that we don't go as far so that we stay local. So that's exactly what this was doing. Same exact problem as the orange one above, but now with the backtracking line search, you don't step nearly as far. Because like going way up here, above that line in that cartoon we showed, right? Like way not the right answer. So you like end up being more conservative because you have this like tangent here. Actually, let's just draw it. You have like a tangent here. You weaken it slightly. Oh gosh, that was terrible. So you weaken it slightly. So let's say like the tangent was like this instead. That's that parameter. And then anything up here above this is not allowed. Anything below this weak tangent is valid. So that's why you end up here and not up here. So that's backtracking lines. Cool. Okay. Let's clear those. Okay. All right. That's everything I have for like gradients. Now I want to talk about constraints. So constraints are a little bit different because now we have to have something that's like gotta be true, right? Like the objective was just like a nice to have. Constraint is like have to have. So how we're gonna handle that is we're gonna basically put that in the cost, but we're gonna do the following. We're gonna do, this is unfortunate that I have double projector and no math space because I forgot to include this. We're gonna write like a really big equation, which is, if you've been in a classical mechanics course, you know that you can take a constraint and you can add the Lagrange multiplier. That's what we're gonna do. And then we'll talk about this Lagrange multiplier a bunch of times and how it changes and how it's different. But like the core feature, this thing, its responsibility is when you take gradients, this deals with like the direction that like leads you to violate your constraint, and it pushes the other direction. So in like classical mechanics and stuff, this would be like the condition that you know, there's a floor under me or there's a wall here. This thing is the constraint that you have to be bigger than, or like you can't go through the wall. This thing, that's the normal force saying that like stay on that part. So like it's actually going to be something that will move and adjust to counteract how hard I push, right? So I'm not touching, no need to have it on. Touch, push harder, it's got to go bigger to offset that. And that's what's going to happen during the optimization. So that's the Lagrange multiplier. We're going to see this a few times in different contexts. So like, we're going to set this up with the following, a 2D problem and a contour plot. And we're going to do, this is just, we'll see it in a second, but it's just like a bowl with a shape. So let's just look at it. Okay, here's our shape. It's a bunch of contours. Here's our constraint. It's this black line. So we're going to talk about like how to solve this problem subject to the constraint that we stay on the line. So roughly, right, like if we're trying to dig out where the heck the right answer lives, somewhere like over here, right? Like, I don't know. I'm going to draw the circle even bigger because then I can't be wrong. It's like way, you know, in this zone. Because like here's the happy minimum, but we got to be on the line. All right. So that's what we're hoping to get. Yoink. Out of there. Okay. So here's our, oh, I did include, okay. Nice. Look at that. Perfect. So you would not be surprised that the first order sort of like condition for making sure that this is at a minimum is the gradient equals 0. All right, we covered that. Now, though, we have two. We have that we want the normal force or the Lagrange multiplier to be 0. That's equivalent to the constraint being satisfied. And we want that basically x is at a local minimum. Okay, so the game here, these are called the KKT conditions, up to some finesse. And this we'll call the KKT matrix, or basically like this is just Newton's method. So what we're doing here is we're just going to apply Newton's method, but now we have x and lambda instead of just x. Otherwise, the same exact setup. So we just ended up with a bigger matrix and a bigger gradient and a linear. We have to solve this matrix equation. Remember, I was like teasing like Newton's method. We like had a 1D problem and then it was just division. But like in general, it's, you know, the Hessian inverse acting on the gradient. That's exactly what this is. So is everybody clear? This is probably the only actual complicated thing that we do 10 times over. So it's not that wild. We're just going to take that step. Set it up, solve it. Should look exactly like what we did before. Take the step. Sound good? Give it a go. And I guess you won't be surprised to know that like things are going to break. So be ready. And then we'll talk about why. But so far so good. Not terrible. Oh, I am not going to be able to fit. Hold on. We got to go a little smaller this time. Okay, so we took a step. That looks like progress. Even better, progress, and we're moving closer to the constraint. Okay. Okay, now it was going so well. And then we're just kind of stuck. So the goal, right, was to get over here. We didn't. Any thoughts about what happened? Yeah.
So the Lagrange multiplier method says that the derivative of the constraint function with respect to, I guess, k or whatever the constraint parameter is, that gradient has to be parallel to the gradient of your function, and it's getting stuck around the point where they are parallel. That point right there has like your contour lines here and your constraint function are kind of parallel. It seems like it's getting stuck
Yeah.
there instead
Yeah.
of finding on the other side.
Yes.
So this is like a local minimum, kind of.
Yes. And said another way, we had an eigenvalue that was not positive definite. And so Newton's method broke again. But yes, like the intuition of like parallel is exactly the correct thing. Let's just though look at that KKT matrix and just like look at some of the eigenvalues. So this is kind of like the structure of this problem is it's a saddle, but like that's a problem because it means that like everything we were talking about from before comes back to bite us again. So how are we going to fix this? So if we have a negative eigenvalue in Newton's method, we need to add numbers. That's exactly right. So we're going to regularize again, but in 2D, so it's going to look different. Okay, let's do exactly that. Check it out. So regularization, I'm going to add a diagonal with that beta. That's it. I'll do it. And then we'll give it a go. Cool. Okay, new version, regularization. So remember, two things we know. It might go a little slower, but it should hopefully fix our problems. Let's see. Whoa. Nice. All right. That's it. Same game as before, regularize to fix your problems. So the lessons always carry over, but we got over that exactly as described, that issue with the constraints, which like we fixed by just dealing with the eigenvalues. Cool. Okay. Oh boy. This is actually great. We're tying off here at a good time. There's a few other things I want you to get from just like optimization, and then I think we'll take a break. Just kind of like get our ducks in a row, but like this piece is important. If what's up?
Don't the same issues with the regularization parameter magnitudes to play a role here?
Yes. So a few games here. So we're actually pretty stable when it comes to so we do need line searches in stuff like this. That's going to come back. We'll talk about it with trajectory optimization because like here we're pretty okay. But like when we go to, because the steps were kind of tiny, as you can see, like we were in a bowl. Also, like I didn't add 2 local minima. We have the same problem with like line search and like crazy jumping if we had like a bunch of like pockets to fall into. So I hid it and stuff because I didn't want to do it. But we will talk about that with trajectory optimization. We will have to have line searches when we do the sort of like second lecture, which is about like how do you do all of this stuff for a control problem. Nice foresight. Yes. So I cheated, I lied to you, and you called me out on it, which is fair. The only other thing I really want to hammer home here is like, if you have the super nice version of this, where everything is quadratic and your constraints are linear, then when you do this Lagrangian, we can do the math by hand, it ends up looking like this. This thing is then totally done in one step. We don't need to iterate like we did before. We don't have to worry about line search or anything like that. If it's this setup, we're done. So let's just like kind of sanity check that. So I don't have any steps. It's just done. So I had a quadratic, but instead I had a linear constraint. Boom, one step. I didn't have to do any stepping. Just solve that matrix equation. Done. That's one thing I wanted to say. One last thing, which is related to this regularization question. I'm going to do some scrolling. Sorry, bear with me. We got to go back to where the problem was hard because I definitely hid something from you, which is we were just like, here's this matrix equation. Who cares? Whatever, right? This thing here, we're going to talk about it now because like it has a lot of stuff going on in that it's not just like the gradient of the cost, it's the gradient, like it's got gradient with your constraints here, and this thing can get like big and painful. So that's what I want to just look at in more detail. So let's go down here and give you one more thing, and then we break, which is, hey, if I do this chain rule, I get this term and I get this term. This term is vector calculus nonsense. This term is like the nice cost function. So like, great. Let's just not do this. And then we'll call it something with, important names. And then that way we're not in trouble when we get rid of it. And it turns out that, and I think rather than go through this, but basically it turns out that when we follow this exact logic, like we can connect it to like least squares and stuff, in order to just say like this is smart and good. But like I think just basically like, hey, get rid of this and just treat it like this cost function. Don't distort the objective with this thing. And essentially, if you recall regularization, it's just like adding stuff to like the diagonal. This is very similar in that it's like kind of a regularization on the problem. So what do I mean by that? Let's just see if we get rid of that term. So we've now like made our Hamiltonian or our Hessian, the KKT matrix that is, simpler by dropping the plus here. So we don't have that anymore. We just got the simple part. Up here, there it is. Just the simple part. And then we're going to do the same thing. And we've got it. And then we're going to see what happens. Awesome. So we got through that bad zone with all the eigenvalue nonsense that was kind of messing us up just by making a simplifying assumption that got rid of basically the hard part of that like complicated derivative. Gauss-Newton approximation basically just throws away the need to calculate like detailed sort of like Hessians with the constraints and stuff. It just says like, I actually am just going to approximate my constraints with like gradients or something only. Yeah. So.
Since it's like, why is that destabilized? You mentioned you could get rid of it and it improves the stability. Is there like, do you have an intuition as to why that term is stabilized?
It's basically the fact that like here's a bowl kind of around your cost, and this is kind of distorting that, which allows the eigenvalues to end up pointing in directions that aren't that like quadratic, and so you can end up with like the opposite sign from this term. So you can think of it as just like adding almost like on the diagonal, or like giving you that kind of like nice local bowl. That's I think like the most concise. Let's see. So like, I guess the other way to potentially think of it is like, yeah, I mean, I think that's like the main thing to think about is that basically like it's a distortion of that like nice bowl around your cost, which is like the feature that you like are kind of like trying to follow. And so like life's good, right? If you like, so if you're following that like gradient downhill and you don't have that like sort of destabilizing force of the constraint function kicking you as hard, then you can just go downhill. And so that's kind of like what you're basically doing is you're just kind of like getting a better bowl and not being pulled by that constraint as hard. And it's like roughly equivalent to like, yeah, a regularizer. So, and I think I could probably finesse that better, but like, I think that's like the sort of cute version of the answer. Yeah, you could probably like formalize that. I thought about it a little more, but yeah, that's the kind of the intuition. So curvature information, and okay, maybe another way to say that approximation, it can cause trouble if you really are exploiting like Hessian information and you really want to manage constraints and keep them like well satisfied in like higher dimensional problems. So this is like a great way to sort of avoid those issues, but it is like, it can be like similar to over-regularization. It can lead to very conservative steps or like prevent you from kind of like doing what you want to do. So if you are in like a big space and you're like managing constraints, you might want to keep Hessian information. And I could comment on like where that has shown up for me in control problems. But like, yeah, it does actually like show up if you do like Hessian approximations versus full proper Hessians. Yeah.
So we're not taking it to be small necessarily, because there's no guarantee this.
Right. Yeah. So the sort of narrative is that like it is small near the solution. Should be. Because like, right, the constraint should be good. And so we should be like basically A-okay on like these things. But there's no guarantee that it is small. It's just kind of like it should be. So it should be like the approximation. Yeah.
So this is like an algorithmic choice we're making. Make
Yes.
life easier, not a mathematical, like it's small everywhere and we can.
Correct. Yeah, it is basically like adding a regularization. It is like an approximation. Exactly right. Yeah. So
I'm not sure my question makes sense, but you mentioned that cheating, like getting rid of this term, corresponds to sort of a type of regularization. Are there like more ways to regularize, and do they like affect the way you get to your minimum? Or
yes.
okay.
Yes, and there are different ways to solve what we're going to talk about later. And I want to break, but like there are different ways to manage. So we've only talked about equality constraints. It turns out that like everything is super easy with equality constraints. But what's really hard is like when the Lagrange multiplier is like on, and when like you have like an inequality constraint that's like, what happens if like this is your constraint? So in this case, you have to manage this in some way. And you know, when you're at equality, when you're at the bound, you want this on. But when you're like satisfied and it's already feasible, you don't care if it should go off so that you can like navigate freely on space. Managing that parameter and doing that optimization in a smart way is a lot of machinery, and there's a lot of different algorithms, and like we'll talk about one of them, which is interior point methods. But there's like there's penalty, which is basically you just do this and then you manually tweak the thing. Don't do that, it's wrong. There is trust region stuff. Or no, we want to talk about this as active set. So you basically just like you find out which points are in and which ones are out, and you like manually turn it on and off. Those are pretty good, but it's like a lot of like extra thought. And then there's two. There's interior point. I'll write it out for completeness. This is what we're gonna do. And then there's augmented Lagrangian. This is like chemical process engineering and stuff in like the 90s and 2000s, like just really like cracked this open and like did a bunch of cool stuff for this to work. This is like just nonlinear programming. We'll talk about it. This is close to the like quadratic program, like Newton step that we talked about. This, awesome, super efficient because you basically get all the perks of here and all the perks of like low memory and stuff. Hard, annoying, kind of finicky, but like not that hard, not that annoying. But like this is actually what like the control software, both of these are in there. This is just a lot more manual engineering. This you can just grab off the shelf. So we're gonna play with this one after. But yeah, so this is all for managing like as soon as you go to this version, you can't just do Newton step and just like magically get it to work. You need to manage the fact that the constraint is not always on. So we're going to cheat and just like, well, not cheat, we're going to do what everybody does. And we're going to grab an optimizer off the shelf that manages those for us. And we'll talk a little bit about like how that's done. But you can think of it as just like, it's managing the Lagrange multiplier. And it's doing it in a very smart way, which is like log barrier methods and stuff. And we'll talk about it. But, you know, that's kind of exactly the set of available methods that people have. Okay, I feel like we've done an hour. that is, I feel like we've done an hour. That's a lot of me talking without a pause. So I think this is nice. We're at a stopping point. I have like 2 more things, which we should definitely have time for, but let's take like, I don't know, what do you think, like 10 minutes? Take a breather. Sound good, everybody? And then we'll come back, do some more. Okay, nice.
And it was fun, guessing. Oh, you did the bad one?
I thought it did.
Yeah, but I would have liked it.
So,
So I found where we think this, where
oh, I
saw
love it. Yeah, we can talk.
the constraint is on, and then I saw.
Way back to the session.
Yeah, it's literally like,
Like I said, only. Is that
I have the
Okay, but you go outside.
Yeah, this was like, the things had to be. Yeah, just like with solving.
so like,
and then
this is
verify
picture your program.
So you learned something.
No, I mean, that's what
Still to lunch.
Oh, yeah, so. Sorry, I just forgot.
the second order method here is it's reminiscent of LBMGS. Which is like, it's a second order optimizer that.
Sure, you are joking.
Yeah, is the naive way, and then the atom optimizer is like the gigachat.
We're all forcing together and then explaining him the problem. Do it. And then the easiest thing, no, it's easy. I said it's good. It reminded me of this says like they would sit with mathematicians during a tea break, and every mathematician would be like, if someone is understanding, oh, like it's true. If I was like, actually, it's trivial. So then the joke was mathematicians only prove trivial things.
When your constraints are yeah, so it's the same idea. It's like, okay, my cost.
This is just.
I
know,
Replace
but
this with the.
So you're gonna get the doctor method. And then
That's not making.
It's kind of funny that it like does deliver.
You are like a redundant. I think once where is the best coffee? Is not answering questions and I don't know.
I've been holding off.
And it is sort of like it's like
We're leaving the afternoon. Might as well. Should have gotten my iced tea. This guy does something.
They're like, okay, evaluate all these optimizers, write them up.
Yeah.
And by the time.
This is like it literally says.
So you just said no gradient to set.
I don't think a Hessian matrix
At all?
This year.
So what LBFGS does.
Is there some reason or?
It approximates the Hessian robot.
Try it.
And
So I was like,
we'll
okay, I'll
use it
try
and
it.
update it and then throw out that red, so it never actually.
Which is fun, because like, it was like a CS group.
And I think I can do it.
That's way long ago from.
So like, it wasn't like physics as much as it was like how'd you build computers, think class. Like,
Join Suraj group.
Or maybe increase one more, you know.
So they're both pushing
Yeah,
and
on the
then
same rate.
and then I'll think I'm blinking.
Morse code.
Yeah,
Maybe
exactly.
quantum in Morse code.
You're actually talking to the cameras right now the whole time.
gate control, air
What's the movie? Lucy.
I think there's a
Oh, yeah, she looks so
And then I think
potentially now she's controlling everything.
I only did a postdoc in that group, that stuff. Like,
It reminds you of, have you seen the Big Bang Theory? You know when Sheldon drinks coffee the one time when they're making penny blossoms? And he's like,
Yeah.
Something I will definitely use.
It's use that.
Yeah.
The best part of Lucy is when she's typing two laptops, I'm like, what? How?
For that.
Anything you could do with two laptops, you could probably do with one.
Maybe.
I know.
If you're
Just
that
about
powerful.
nothing bigger.
I mentioned this at the start, so like
Yeah, that'll be super.
Well, I think that's a dangerous precedent. Like if someone is actually high, they would like Southeast Asia, like put some drugs in, maybe I'll unlock some potential.
so these come from
100% brain. And they are
I don't know anything there.
put some drugs in.
No, there was that other.
Any quantums.
so this is kind of
Someone
like
was thinking
Like
of
the
the-
Limitless.
Oh yeah, that one. Yeah.
I've seen
They
that
also made a
one.
TV show.
so it's like
But
I think one season after no one watched it.
I knew it was
Like we know the
fake.
plot.
I knew it was fake when he just started doing stocks. I was like, okay, this is like, even if you have 100% brain potential, I don't think. Was that?
But you don't know. You don't know.
I mean, but isn't that the thing like, so
right
Jim
now we're just
Simons
doing
made
like
his money that way?
I don't think that is just.
Like Simon's Foundation, like the quantum, he,
Oh, Renaissance is this, right?
Huh?
Renaissance is this.
to make it.
yeah, I forgot what his actual, I think it's Renaissance technology or something like that. He was the richest mathematician in the world ever, like billionaire, because he, in the 80s, he basically used stocks. But the issue is, anytime you predict a stock, or anytime you fix it, like let's say if you know a stock is going to go up tomorrow, you'll start buying it today and it'll go up today instead of going tomorrow. So anytime you figure out a pattern, you fix it unknowingly. And so that's an issue because like you can never, that's why you can never be. But in limitless, that is the opposite. It doesn't work.
So
Because if you know something about the market, if you know the prediction, you can start doing it today. And instead of it being a prediction, it'll happen right now. And then it's not gonna happen in the future. So yeah.
Oh, yeah, yeah.
yeah, I don't.
It's also going from first principle. So.
It's all numerical simulation. I was wondering if because in quantum ML, then you can maybe figure out another way of this. You see what I mean?
Maybe
Like
they're
make
doing this in
billions
like little more countries.
Probably. I wouldn't be surprised because that's how they did in the 80s and the 90s. I
There's the
wouldn't be
next
surprised if they
version.
did the same thing. in quantum.
I think it's
Better simulations. That's how the stocks are priced using the simulations.
More so. GPU, because the GPU can do
Not like that.
yeah, it's like and so yeah, so they are
They're like your.
figuring out that way to get this.
I'm just gonna start being like this, that way it doesn't have the option to twitch.
We were saying,
It's just closed.
have you seen the movie Lucy?
So what?
Lucy? It's Scarlett Johansson. It's like she unlocks her 100% brain potential. Being,
Not having seen
I maybe are heading there.
It's like 10%.
Yeah.
By the end of the day, she'll be like two laptops.
She can control radio
So
waves.
you don't need any laptop.
I can understand.
That is good. I like
You really?
And that's a
I didn't just-
kind of weird movie. Like the ending was like, I was
just
like,
thought-
wow, okay.
She just.
It's just called Lucy.
Yeah, it's funny.
Her name.
Yeah.
Like cancer.
No, I think her name. I think it's like
It's
the,
about three volts.
you know, that book about that first.
I never remember what
primate or something.
I was talking.
That's a friend of
mine.
Oh.
It does say that's her name.
Oh, it does.
It's major. And she's like, yeah, I just won 7 calculus classes. I was like.
So that could be why they chose the name still.
7 calculus.
You're right, the first primate was Lucy.
Count
right?
two.
I think so, something like that.
Differential equations, you count back that.
There's a book about
It's
something.
okay.
Or not primate, I guess the first human.
Yeah, I think in the evolution of
Other calculus is there.
Okay.
Which would make sense, because then if it's like.
yeah, then she's.
In that case, then every engineering course, basically, this is how it's going to be.
two students.
Gotcha, and so you did solve this,
So you had to solve this, yeah.
but you probably made this approximation. You're thinking.
Yeah.
That's the thing, it's crazy to be on papers where you're like, I didn't tell you the results.
You might be like, yeah.
But I didn't do the calculation.
What are you doing? Like, wow, yeah, well, no,
Don't use it.
I like it.
What's up, like, seen anything like guys like 100 brain power and I'm
Yeah, we
like,
are.
I use this 1% brain power or something completely like
Yeah,
that.
it's got a priority.
No, but how can you insert the package?
Oh, this
Airport DN.
Oh, that's very hard.
Judging from the length of the index.
What happened? Oh, where's you know where's Jose?
He never attends the first session, so I
Yeah.
feel like.
Because he doesn't wake up. Like if they
It's
start
like
at
he lives in
10
Northampton, it's like a 20 minutes drive and he takes the bus to get here, so it's kind of comes in with his bus schedule to get here very early.
And it's like first order.
Well, that's because actually it was 7.7 magnitude.
Oh yeah, in Venezuela.
In Venezuela, right? Yeah.
Oh, in Venezuela.
Yeah, we'll have to ask him.
Yeah.
I guess he doesn't have
He
family
doesn't
there
have any
anymore,
family
but
left there, but
he might have, he might have friends, I guess. I don't actually know when
He moved down there.
And you say,
he considers it home.
and if I'm not going down, then cancel, you know, so, there are firms that is sophisticated.
He's looking.
And then Gary just has you and then Donald has you and Michael part-time.
So then what do you do? It's like
Already estimating.
Hey, you guys don't have like any.
they're saying now passport is to prove your identity and so you can't use it to buy
So is
anything
my
online.
Army.
It's like what I said, how do
I don't know. No, they didn't specify
Yeah.
what it.
I don't know.
What
Once
they
it's
want
done,
to
Well,
get voter ID
stop
card so
the
then they
saying
can.
that.
No, no, but their point is voter ID itself is like
But
RB
without your
civic
start.
I guess. So it's a SIR money.
I was thinking.
So then if like if that itself is problematic,
It
then you have
is.
to find out.
Are you going to?
What is that thing? Passport is not
Yes,
in material.
I know that.
In genealogy.
Yeah.
Because you know,
Hey, so Rob,
some people.
ample.
Oh, yeah, so then it's like, then what I do?
So send us a few notes.
I don't get the CJN, and then they
Negligible dimensions. There will be 1 million.
That's not used in
Half of your
people sell it as
So that's why I'm depressed.
I used to have a lot. So yeah, Kenneth.
Pretty tricky, so that's why
you know,
But did you ever?
And possible. 11th, 12th, 10th, 9th. From the 80s. 16 to 20. That's what squash now. Debate.
10,000 processing 1 billion.
Debate competition.
I think 1 million.
Based optimization, just.
When I pay 1 million, this will be
That's
I should get something. Platinum stages.
Speech and Punjab school.
Then why would everybody want this?
Okay. National Bank. I have got.
You trying to get one?
Without being subjectly used that or not used. Sure, I guess I don't know. But I guess if you have like 4 or 5
So every time, so I decided I should use it.
and like, I make money elsewhere, but I just want to be here.
Software, I always have like the serious things where
Funding.
It's a textbook, it's not like fictional book. You mean? Yeah.
And
Those are both.
like the box and the threads.
And I want to put on to
can I, sorry, I need a second. Safari's not even the reason why this pops up every 5 seconds, so I still don't know. Because I went and checked and it's fine.
I mean, Safari and Apple wasn't running natively in the ARM based.
No, but what else do I have open all the time? So I was like, maybe it's okay.
We tried it last time, but I realized what it was. I was just having my
I
initials
have not
last time.
updated it from
Use that.
should be QA.
Yeah. I tried to make one yesterday, but my
Set me back. You know what, maybe that's like.
Oh, I don't have service. But I can put it.
Do you use it?
Not smart.
But do you back up to something at least?
Yeah, I have my.
You know, play without his queen.
I played
Also, search for many. Because like I think like we would play like one regular game without
Okay. I think, let's see. Are we, people are still out in the hall.
Send me a message, send me a
But
message.
this is German. Allow all the forces are done.
I think we can kind of like spin things back up. All right. I'm gonna get kind of like back into it then. We're gonna do 2 more things. So the first thing I want to do is I just want to give you guys like a flavor for optimization before we hit like control, just so you can see it in a different context. That's this notebook. And then we're gonna talk control. And I'm gonna squeeze in like a short demo after that. So that is a lot. And I realize that my time is quickly running away from me. So let's try to do it. I think this should be pretty straightforward and could be messed with, but like I really just want to hit home some of the like things that we were talking about, and that will tease what we need for the next section. So one thing you can get from what we just did is like things that are pretty straightforward in a lot of different contexts, which are like least squares. But then we're going to add other features to that to remind us that we want to do optimization under constraints. So the problem we're going to use for this is tomography. And in particular, I want to reconstruct the density matrix. And I want to do that from a set of measurements here. And these measurements are, we're just going to pick some. There's some choice on the hardware. And you get probabilities. And these probabilities will be noisy. So our kind of gimmick is going to be, if those are noisy, how do you make sure that you get kind of the best density matrix? And then we're going to talk about what that means. Now, of course, we know things about the density matrix. It's not just these 4 numbers. First, it's symmetric. Second, probabilities have to add up to 1. And third, probabilities can't be negative. I mean, yeah. So we need those features for it to be like a good density matrix. So we can do a few things to set this up. Make some states, and then pick a state that's going to be the ground truth or like secret. I don't know. I just picked some stuff. And then we need the projector. We need the like to do the trace stuff or whatever. So we got that. And then we're just going to measure to get some data. So here's our ground truth probabilities. All right. We measured the ground state, the excited state, and then plus and minus the x eigenstates. Cool. There it is. That's what we're going to be trying to get. Okay. Ignore contrived example. I was messing with stuff. We're going to add some noise. This is basically just like I've got measurement noise, right? Like I measure probabilities. You have shot noise when you run an experiment that you can never get rid of. It's finite statistics. And then you have some probabilities that aren't going to be the exact things. And maybe you're just like, you know, okay, some nonsense, but like, we'll deal with that. So the dumbest, easiest, most straightforward thing to do is least squares, right? Like just make these match. There's your cost function. That's exactly the kind of thing we were doing earlier. Just like make these two things equal to each other. I'm going to do this in jump. So I'm going to make some variables. I'm going to encode my symmetry in the free variables right off the bat. So there's my density matrix. These are now the variables I want to solve. The only thing I need is these residuals, right? So I have measurements. I have the density matrix. I take the trace. I subtract off the probabilities. And these are my residuals. There's my cost function. Sound good? So we can grab this. We can run it. We get a density matrix. Okay, cool. We can check. And it's kind of like sort of the thing. Remember, it was noisy, so we're never going to get perfect. And like it has our baked in symmetry constraint. Cool. But okay, so the probabilities didn't add up to 1. That's a drag. We actually got lucky here. Cool. Okay, so the I like positive, that's half the battle. We got lucky, but like we can't always count on getting lucky. So add the trace constraint. This is exactly what you guys already know how to do. But now we're just going to kind of short circuit it a bit by adding it in jump. That's it. Okay, so we got a linear constraint. You could do this with the KKT system and all the stuff you just did previously. You could set this up and solve it with those little functions we wrote, and you would be able to derive this problem yourself. So if you're, I don't know, you want to just like mess with something, there's a thing. You could try that. But we're just gonna shortcut and grab it. So we do it. There's another one. Okay, you kind of get the, you know, the bit now. And like, I bet we know exactly what's going to go down here. Nice. So like, of course, now we got constraints, which is key when we want to solve problems that have to have constraints. Okay. Problem. We didn't ask for everything. So because of this constraint, it shoved us into a space where these broke. So of course we have to ask for all the constraints or we don't get what we're looking for. So yeah. So okay, so then yeah, what do we got? One more. Positive definite. Now this one, it's a bit weirder. This is new. Because if you're going to get this for a 2x2 density matrix, it's basically like these two eigenvalues and then something about the determinant. That's nonlinear. So that's weird. So like our KKT game from earlier, we wouldn't actually, without some extra finesse, be able to handle the fact that these are both inequalities and nonlinear. But we're just going to brush that under the rug for now and say, well, jump can handle it. So we'll put it in here. And then what I talked about earlier, we're going to leverage an optimizer to manage this for us. And so we're just going to see what happens. Oh, wait, I don't want this to talk yet. Okay. Another one. It looks like that. Okay, I don't know. But, oh, we forgot to check properties. Shoot. Of course, this is definitely true. Nice. And believe it or not, it handled that as well. Okay, great. So that's much closer to like what we were trying to get, right? Which is, this is a pure state. So cool. Okay, that's numerical noise. So like, not worried about that. And we can check like, okay, you did better. You know, like you could do some denoising or other stuff, or like try to be smart about like managing or adding measurements, blah, blah, blah. But like the core feature of like this is like now you kind of know how this is working under the hood, which is approximately exactly what we talked about. For the linear constraint, it's exactly what we talked about. How do we know? Well, let's do two things. Put this in, and actually we can do that for up here too. Okay, so I'm going to print some stuff, but I want to show just one thing. So this took one step. That's pretty great. Why? Well, let's look up here at this problem. So this is essentially a like quadratic, and this is a linear constraint. Quadratic, linear constraint. We saw that like when we wrote the QP down and we did Newton's step, one step, right? So one step. Cool. So that kind of sanity checks out. We'll talk about what these outputs mean otherwise in a sec, but like, okay, objective goes down. Great. And if we do the other thing for this one, more than one step. Because it was nonlinear. And so here's where we can start to look at a few features of this that I'm going to tease for later. The objective goes down. This is how good the constraints are. So you can see that at the start, whatever random density matrix it picked, and like the probability constraint and all that stuff, junk. It's a big number. And then it immediately deals with satisfying the constraints, and then it's good. How does it do that? This dual here, this is the size of the Lagrange multiplier. So this is the size of the objective. This is the size of the F, the constraints, how satisfied they are. This is how big the Lagrange multiplier is. So what it does, it's got some initial problem structure. Lagrange multiplier gets big. Normal force goes on to sort of force you back onto the constraints. And then it gets small again because it doesn't need it anymore. This is like the secret sauce I was saying about like managing that penalty for you, so you're not just futzing with it yourself to try to get it to work. So that's the game here. So this under the hood is doing all of the Lagrange multiplier stuff to deal with the inequality constraints, et cetera, et cetera. And that's basically the game. Oh yeah, we're not probably not gonna do these things, but like, okay, yeah. I kind of already teased all this stuff. You could just mess with things. I also kind of cheated a little bit in that I didn't want to have complex numbers in here, but like you can imagine, we'll talk about it later. You got everything has, you know, real and imaginary parts. You got to like optimize both of those pieces, et cetera, et cetera. But that's it. Like that's like you've got the toolbox now. You kind of know what the pieces are. You understand there's Lagrange multipliers to deal with constraints. You understand that the constraints need to be satisfied. Objectives and constraints have to trade off in some way, and the Lagrange multiplier is kind of managing that force for you to deal with that. Okay, so that's basically the whole game. Everything else is just about tricks to do it faster, or more carefully, for some version of faster, careful trade-off. Okay. Oops. All right, so what I want to do here for like the next section, I'm going to cover how to do this for control. So that was like the big teaser. So we're gonna hit control, and then I'm gonna plug like a little bit of quantum control stuff and show some cool animations, hopefully. But we're gonna play the same game. It's basically just there is control. It looks exactly like optimization, but now there's more stuff in the way. And when the problems get bigger, because you have this like whole object to optimize over, how do things not blow up? What do you do that makes things sort of stay safe and stay nice? And like the key feature is going to be problem structure is everything for these problems. The fact that like dynamical systems go forward in time means that like there's something structured about that. It's not just neural network with big pile of parameters. It's like a very like temporally ordered problem, and we're going to use that to our advantage. Okay. Yeah. Okay, so here was our thing from before. Remember this? Awesome. KKT conditions. Now we've got a dynamical system which has stuff goes forward in time. You got a bunch of knot points here. Each of these is like state control. And if you look, we can set up our problem. Yeah, what's up?
Before we move on, I just had a quick question on the density matrix.
Oh yeah, for sure. What's up?
So the constraint that you put in for like the trace preservation and positive probabilities,
yeah,
this alone doesn't fully constitute a physical density matrix, right? Because I can still have something that follows these, but it's not positive semi-definite. So normally I would have to actually diagonalize and get all of the eigenvalues of a density matrix to make it completely physical. So is there a way to impart this constraint? Because this would not be a linear one that you could just put in with a Lagrange multiplier.
Yes. And in fact, that's exactly why we have this weirdo determinant bit. That's doing exactly the positive semi-definite. I just didn't derive it for you. So I kind of like, I kind of snuck that one by you, but like, you're right.
Okay.
Like, in fact, you could do this way smarter if you realize that you're like over a space of like matrices. And then like, this is like, I was doing it over like this list of parameters, but you could switch to like Clarabelle or something and solve this problem in a different way by putting yourself in like a cone and doing like a second order cone program and saying other words. But like you could flip the optimizer and the structure of the problem and do it more explicitly and correctly.
I see. Okay.
But you're totally right that like this is a 2x2 sort of cheat.
Yeah.
This technically you could play this game and kind of still get there. But yeah, like it's non-trivial to impose that constraint. It is very nonlinear in fact. But like, yeah, that's exactly why you need some nonlinear program. You know, you need to do something smart to play that game. Exactly right.
I see.
Yeah. Nice. Yeah, I think that's really important. And like I said, there are other ways to do this that are smart as well for those kinds of like, so if you look at like Clarabelle or something, you could see like another way to do this problem. So that would be like a good exercise. I could put in the like little exercises section is rewrite this by learning that and doing it again. So now it's on your homework. I don't know. Cool. Yeah. So we're gonna have the same problem here, like F not linear. So we're totally in the same boat, right? Like we do not have the ability to do this without being smart. So that was the teaser for why we were getting that feature baked in earlier. Other thing I want you guys to see from this before we like do stuff, look at the fact that this is like local in that it's not just like a big smash of like all of the ways X could couple to other time steps and things. It's like each individual knot point is sort of sitting by itself safely, or they're just coupled to nearest neighbors. That's absolutely essential. We're going to cover two ways to handle this. Indirect trajectory optimization. We're going to basically say, okay, there were states, there were controls. I don't want to deal with states, throw them out. Direct optimization, we're going to keep the states in, and we'll talk about why that might be better, what price you pay, how to survive paying that price at scale. So, and I guess Michael's gonna live. Yeah, he's gonna hit you over the head hard with indirect trajectory optimization. So yeah, you're gonna learn plenty of that later. So I'm just gonna basically do Newton's method because I'm a coward. So check it out. F equals ma is as fancy as we're gonna get. So we've got a mass. Oh, I put it twice. Oh, that's so awkward. Ignore that. It's over here. It's not. I don't know. Well, it's. I think that's actually right. Now that I think about it, yeah. We're fine. It's right in here. That's what's key. I think I do need to remove it and divide it. Yeah. So the core feature here is that we have f equals ma. This is our state. So we have the classic like double integrator problem, which is that if you look, basically f equals mass times acceleration. So like mass times acceleration equals my force. That's the external control I have access to. And then this is just like momentum conservation, like velocity. Yeah. So that's what we're working with here. It's just the double integrator. So if I look at basically this dynamical system and then I just approximate it with the identity and then a little step, and then the control bit gets a little step, then I have, like some version of this system that I was describing above. So I guess like I just want to say like here's A, here's B. These are the two matrices we're going to need for that dynamics constraint, which is AX plus BU. So AX plus BU is our relatively straightforward linear constraint between the two knots, right? So X dot is equal to some matrix, or Z dot is equal to some matrix times Z is going to be kind of our structure. One thing I really want to like highlight, and we'll hit this later, the kinds of dynamics we care about for linear systems are matrix exponentials, right? So X dot equaling AX or Z dot is equaling AZ means that you have like a matrix exponential for some tiny little time step. And there's this fun little trick that you can kind of derive that just says like, oh, okay, like if you do the series, the sort of single time step shows up here if you compute this exponential. And that's going to give you something which is the full like nonlinear series for each of these terms. And that's a first order approximation to that is this like Euler step version that we just showed. So what I want to just emphasize is like when you discretize systems, solving the ODE in a smart way might matter a lot. And you are like always making approximations and you can do a lot of smart stuff. And like SciML, if you just go to their page and look at like their list of integrators, you can live like in that for quite a bit, just like exploring different ways to like forward step. Yeah.
Is the top one, the AH and the BH? What is that like the just like the first step? No, in the very top one.
Yeah, that's this. So AH is this.
Okay.
It's like the full. No. So you can derive
I was
this.
wondering if it's the first step of the or like the full expansion. It makes sense. Thank you.
Exactly. So if I like do this exact thing and I like compute the exponential and then I just extract those pieces, we can like just check and you can see like, hey, here was the matrix trick, here was Euler, and check it out. Like there's this like tiny extra bit that like wasn't in the other approximation. So like getting the ODE integration right is going to directly reflect how well you can control and enforce your constraint, because the optimizer only sees the constraint you give it. So if it gets a constraint that's like kind of the dynamics but not quite, it's going to enforce kind of the dynamics but not quite. So that can come back to bite you, especially in quantum, where you're like trying to preserve the fact that like a state, right, has a norm of 1. It's got to stay, normalized the whole way through and stuff. So if your like ODE slightly grows or slightly shrinks and you don't conserve probability because you're approximating the exponential, you might break a bit. We'll talk about it. Okay, so the only thing we need is occasionally to roll some controls out forward in time. So take some steps, start at 0. Let's just accumulate a bunch of the states and then return it. So this is just solving that discrete ODE forward. So just time stepping Nothing fancy here. We just need it. So let's put that in there. And then here's the first version. This is the like simple harmonic oscillator for control, the linear quadratic regulator. A few things going on. Linear dynamics, that's nice because that constraint is easy. We kind of know how to handle that, right? We've seen linear constraint before. And then this quadratic cost, also awesome. Remember, we talked about like quadratic cost, linear constraint. We kind of are in a great playground for nice problem. The only kind of novel thing here is that we're already baking in our regularization, right? The regularization is living on the controls here, but like that's the sort of QR is like you just kind of like play with the name and you put the states for the regularization or the regulator, the fact that it goes to 0. So we'll be using like delta X to get it to a goal. So X minus wherever we're targeting. And then this U is just the controls don't blow up. Because otherwise, like you would just drive the system as hard as you possibly could to go as fast as possible and it would break. So we can write this cost down. And that's the problem we're going to solve like a bunch of times here. So same as before where I was writing down like here's h of x, we're just going to do it. Now we're going to do this problem 5 times. Sorry. So indirect trajectory optimization is this. It's basically let's just pretend that the states that I cared about, those are just like the rollout of the control. So let's just plug in that differential equation, get rid of states. States, I don't want to deal with them, they're gone. So this is something called like single shooting. You're basically just going to like launch those controls forward and then see where you land and then just optimize over the controls. This is pretty close to grape. Mike will talk about it. So we're going to change the cost function. We're going to roll out those states and then we're going to plug it into the cost. So the only thing we now have is the controls and all the other junk in the problem. Sound good? We can do this with our little handy utility. We're going to have an initial point, which is a position and a velocity. We're going to try to get it to 0. We're going to go back to the origin and stop moving. So we're going to just basically like have a particle or a hockey puck or something that we've kicked. And now it's just putting along with some velocity from some point. And we're going to try to say, wait, stop, don't, and push it back to where it started or where the origin is. So we'll add some shape and then we're just going to solve. So here's our gradient. Or here's our cost, here's our gradient. We're going to call optim. We're going to take some Newton step, but with some just like approximation. This is fine. We could plug in different things here and it'll still work. Oh, maybe it won't. It's math. Oh yeah, I don't reshape things. That's why I wouldn't do this. Okay, so like you could change different solvers, but I didn't shape all the matrices correctly. So the point is now you have the U, which is the only value that you optimize over. And then you can just roll that out to see what you get. And we're going to look at pictures now because this is too much not pictures. So, okay. Here's the phase space plot for that. Position down here, we're at -1. Velocity down here, so you're going in the wrong direction. And basically, we're going to push it because we are going left. We're going to push it right. And then we're going to swing back around to the origin. So we're going to add a force to send it the other direction because we started on one side and we have to shove it back the other way. Okay, so that was it. Like we got this out of that optimization problem. Seemed pretty straightforward. If we look at our forces, you see that like early on, we give it a big shove and then we just kind of like guide it back towards the origin. So that's it. That's trajectory optimization. Same thing we did before. Just solve a minimization problem. The constraint here, we cheated, right? We just like got rid of it. So first, there's only controls in here. That's the first thing I've got. I said that the dynamics are always satisfied because we just shoved the constraint in. and like no problem. The issue is that this is pretty sensitive. So let's say I like just goof and futz with that initial control value. You can guess like that might mess up what we were solving. Let's see. So we're supposed to go here. Totally wrecks it, right? Whereas if I had done like the end one, not that bad. So there's like an asymmetry, right? In terms of like the initial controls versus the final controls. The problem has weird sensitivities.
What were you just changing?
Oh, yeah. So I took the control that I got, my like optimal solution, and I just rolled out that control by like tweaking the final value by like 95%. So I was just like, hey, what if I like just kind of futzed with some noise early on? Like just kind of obviously like the optimal control is going to respond differently. But that also means that like during the optimization, the early points are sensitive for every single part of the trajectory. The late points are only sensitive at the very end. I'm going to show this in another way, super quick. Here. So I'm going to show you a picture. This is that Jacobian. Black points are non-zero entries in the Jacobian. And by the Jacobian, I mean like the response of the state variables to the controls. So you see that like the initial control hits everybody. And the later controls only matter for the, like only impact the cost at like the end. So like, I guess what I'm trying to get at with this picture is basically there's a big sort of depth problem to the gradient information here. You have a very dense Jacobian. And that means that like, if you have an ODE that runs for a really long time, you have a really like layer heavy calculation to get the like way that the controls respond to the cost. So you have like all the same issues of like a really deep neural network with vanishing gradients and kind of like potentially ill-behaved problems. You have like a really potentially big landscape with a lot of nonlinearity because all these controls sort of are talking to each other in weird ways. So this is a potential challenge. That's basically like the point of this picture to take away. Potential challenge because all the controls talk all the way throughout that problem, right? So the initial control has, or the response to the initial control matters for like the whole chain. Okay. The reason I'm going to show this is because I'm going to show gradients later and have a different structure. Okay. So that was like an example of indirect optimization that's just like straight up plug in the dynamics, get rid of the constraint, explicitly enforce it. And that's kind of cheating because like there's a lot of other constraints that we might want, like keep the controls in the bounds, maybe like don't let the states go in a certain region because that region, maybe there's a hole in the ice rink or something and you just have to avoid that spot. So there's a lot of other constraints that you have to watch out for. And so we want a more structured approach to this. Yeah, what's up?
So in the Lagrange multiplier picture is kind of the analogous thing to what you're saying here with the single shot method of plugging straight into the constraints. Is the analogous thing to just like plug in the parameterization of that parabola to your cost function?
It would be like solving for like that's an implicit equation, and it'd be like eliminating variables. So the way to think of it would be like that curve that we had is like a y equals f of x. Sometimes it's like f of x comma y equals 0.
Sure.
And if you can solve for one of the variables, you can drop it, and you can trade nonlinearity for fewer variables, which is usually a trade you can always make. In fact, if you're doing quantum, you're very familiar with like everything becomes an observable, right? Like if you think of like a wave function, it is kind of like a weirdly nonlinear thing, but you just like turn it into a bunch of modes and then it's just like a linear matrix equation. So you just like add a bunch of observables, you linearize that thing, and it's like over a function space that might have a lot of stuff, but you've like gotten rid of nonlinearity. But you can always kind of play that game to go more nonlinear or less nonlinear. And that's actually a little hack for like the tensor network stuff. I think like time-dependent variational principle is basically like starting with a linear system and being like, psych, that's too big. What if it was more nonlinear, but had fewer variables? And you kind of like do exactly that trade. But that's not my area. We're going to pretend that that's right. But like, if it's not, don't yell at me. Okay. What I want to do now is I want to walk back to like the thing we already know and the only thing that we know, which is like do the Newton step, the KKT system, and check it out. This thing here, the LQR, it's a quadratic cost with a linear constraint, which means that, okay, one thing, we have to now find out H and Q and C and D. But if we do, one step. So there's a game to play, which is like do annoying thing, which is finesse all of that into the right shape at the price of big win, one step. So now we're going to just see like the process of, yeah, what's up?
Can you repeat again the components in the LQR objective, please?
Yes. So it's a quadratic cost. It's a linear constraint in the dynamics. So this basically here is saying like, you're trying to go back to the origin. So it's a regulator. But like you could put a delta x and just have an x minus x goal instead. We'll do that later. But for now, we're just going to the origin. So it's penalize that. And then like you see that it's like over the course of the time. And then at the final time, you have like maybe a bigger penalty or something. So it's a quadratic around all the states. So you got like a bowl that just sort of follows the trajectory all the way through. And then you have a regularizer on the controls. So the Q and the R here, they have to be positive semi-definite. And the R has to be positive definite, actually. But we know all of that comes from the regularization conversation previously. And then we have a linear constraint, and that constraint is our dynamics. And so that's exactly quadratic cost, linear constraint, with basically just stacking up all our variables into some z. So if we just put everybody in one big column, then it looks like this. So now we just have to like play the game of put everybody in one big column in a way that doesn't suck. And hopefully we like write good code and like that's what we're going to try to do. So hopefully I don't confuse you. But we're going to we're going to make H, we're going to make Q, we're going to make C and D next. Sound good? Yeah. Okay. So the gimmick we're going to use is we're going to like have little functions that create those like blocks for us. So we're going to have little selectors that grab the indices at each knot. So remember, like, if you look here, we're collecting these knots, and that's like the part we understand. Those knots are like time points. So we're going to just have functions that grab those for the appropriate offsets for the problem structure. So that's what this is. So the first one we care about is the H, which is basically the first control, then the first state, or the start state, the start control, all the way down to the final state. Okay, we're going to make that objective. We're doing exactly that. Loop over all the time points. Put in all the Q's where the X's are. Put in all the R's where the Q's are. Wait, what did I say Q? Put in all the R's where the controls are. And then the final one is basically just about where the goal is. So we'll do that. And then I'm going to show you pictures of these in a second. Here's the constraint. It's basically, if we look at this second row, it's that AX plus BU. So it's if we check it out here, it's AX plus BU equals the next time point, X, right? So X at time plus 1 is equal to X at time T plus U at time T. So we just put that in, and we get this nice like tri-diagonal structure with the initial point kind of floating here as well. So we're going to do exactly that, same game. X u, x at next time point. We're just setting up that exact equation. Okay? So we've got h, we've got q, we've got c, we've got d. There's the Lagrangian. Here's our KKT system. It looks exactly like this. So our job is to solve this equation for z and lambda, where now z is that crazy long list of all of our knots. But it's the same game as before. Yeah.
So are we able to choose the Q and the R then to
Yes.
compose the regularizer?
Yes, exactly. So if we change the Q and the R, we'll change the shape of the problem. And so we'll change the optimal solution. So that's like a really good point. The optimum solution very much depends on the shape of what you're asking for. So if you say like, I really care about getting there as quick as possible, you know, you might like make sure that the trajectory penalizes everybody equally. Whereas if you're just like, I just need to be there at the end, but I want the problem to kind of be safe, you might say tiny q and then giant q at the final point. And like, same with controls. If you're like, I'm really concerned about like pushing super hard until I've kind of warmed up for stopping my hockey puck, then like maybe you put a big penalty at the start while you're like trying to get going, and then you like let the forces turn on or something. So you get to design those parameters. Usually you just kind of pick them to be some constant, but they could totally be different throughout the course of the problem. Yeah. So now we just set up the matrix just like we did before. Grab those things. And we're going to make a QP. And we're going to just solve it. Backslash. Just like before. We're not going to do anything fancier. It's a one shot. And hopefully we just get a good answer. So remember we did the gradient thing before. I know I showed it like it felt like an age ago. But let's just see. We're going to extract the solution. And we're going to compare to the previous and we're going to plot it. So let's check it out. Okay, so basically the same, but in one step. Also, looks good. Just kind of like for sanity, that's roughly what we had before. Nice. So we basically have this like massive linear equation, right? Which is solve this Newton step, where it's like the Hessian from the KKT system, and then all the other information, like the gradient part of the KKT system, and we're solving that linear equation in a massive space as opposed to a tiny like 1D or 2D space from before. So why is this not horribly catastrophic, right? Because if I'm, you know, solving linear equations for a lot of numbers, famously, like, that is an expensive problem that like, you know, has a bunch of issues, like hard to like GPU accelerate, hard to just like get good scaling, right? People really care about solving AX equals B because it undergirds so much stuff. So this one, why it's okay is because remember we had that temporal structure. So here's that C matrix, right? This is basically like the, you know, time steps between the states are glued together and time steps between the controls are glued together. So in our big Z matrix, we've got a lot of sparsity. So that's the key. That's like why this doesn't kill you, is because the sparsity is there. So if I check out H, right, like diagonal, no problem. So the feature that leads you to like not immediately just like die, game over, is like there's so much structure and trajectory optimization that if you were just to have the same number of variables, like if you have 1 million variables and you're like trying to solve an IP-opt like nonlinear program, scary bad. But like if you're able to do smart, clever stuff because of the structure, then you're back in business. And that's basically like, if you think about like Boston Dynamics or like SpaceX or all of these like companies that do control, like they're doing the same stuff, but with like clever little tweaks. Like sometimes the tweak is like how to do the constraint in a smart way. So like for SpaceX, like the rocket landing, it's like how to turn the constraint from something that's like a nonlinear program like we've talked about, where the iterations might like fluctuate, into something where they have a guaranteed sort of convergence path, like a QP. That's the whole game that like led people to be like, now we have to, you know, make SpaceX companies because we know how to do rocket landing because we can solve it. We can turn the nonlinear program to a QP. So now instead of the problem like converging probably maybe, it like will converge and you can get an answer online and you're safe. Same game for like the Boston Dynamics. It's just like I have a like robot with a bunch of sparsity and I can do it really fast online because like I have structure and I can satisfy all my constraints stably. We're gonna do that for quantum too. I promise. We're almost to quantum. But yeah. Okay. Okay, so questions on that. That's like I direct optimization for those reasons. That's what I care about and why. But I do want to say that there are like resource trade-offs. So I want to come back briefly because this is gonna like tease a little bit of like Michael's stuff. Is like there's other ways to solve this problem that have, you know, subtle differences that we could take advantage of. So like we should just revisit it super quick. So when we did indirect before, we just like threw the constraint in there and we didn't really do the KKT stuff and all the like machinery that like made us feel smart and like good and doing the math. We just kind of like cheated. So let's actually look at like if we do the indirect problem with the KKT system, like what that might look like. So this is like subtly indirect, but like this is closely related to, or basically is, Pontryagin principle, but like discretized. So this is a mathematician who like alongside the Americans, he's like a Russian guy who did a bunch of like control stuff during like the early aerospace days as well. He's also like blind. So like I think his mom did a lot of his like writing. He just like dictated and like solved all this in his like head, which is crazy. So pretty cool. What we're gonna do, LQR. Put the Lagrange multiplier up there with our linear constraint. And then we're just gonna do what we know how to do, which is compute these gradients. So you could do this. It's just some derivatives of some linear stuff and some quadratic stuff. So some x squareds and some x's. Set them equal to 0. And then you stare at them for a second and you remind yourself that like this one, for example, the derivative of the Lagrangian with respect to the multiplier, it just tells you that the constraint is satisfied. So that's just the like forward ODE. This one here, if you look at it and squint, you realize, okay, this is basically like previous Lagrange multiplier is equal to future Lagrange multiplier controlled by the state. So this is like a backwards ODE. This one here, it's just telling you how to relate the final to the initial. So this is basically like the initial condition for the Lagrange multiplier for it to go backwards. And this is how to turn Lagrange multipliers into controls. So you can go forward again. Said another way, you've got a forward equation, a backward equation, an initial condition for going backwards, and then how to go forwards again. So you have this like iterative process, backward solve, forward solve, backward solve, forward solve. Yeah.
Is this like adjoint optimization?
This is exactly the same thing as adjoint optimization. This is basically backprop. This is basically how you solve a neural ODE. It's all roughly this idea. Yes. So yeah, like this is like approximately like that sort of family, but like the sort of ODE presentation in terms of like 50s math. I don't know. If you don't discretize this and you just sort of like, I'm a mathematician, why would I be a coward and try to put it on a computer? Then you're actually doing Pontryagin principle and you're doing variational calculus and like, no. So yeah, if like that's like physicists love that. You don't actually ever do that. Like we have computers, like that's not the right way. But like you can, and you can be really smart and do cool stuff and solve homework problems. But like, I don't know, functional optimization is scary. And so I don't want to do that. The main thing I want to highlight here is this is solve ODE forward, solve ODE backward. So you never have this like massive landscape or blow up in memory, which is key. So you're trading sort of some finesse over doing ODEs a lot with basically like a memory limited approach that prevents like needing to store all of your optimization variables and solve this big linear system. So in fact, like interior point optimization, you could do a lot of smart stuff to solve that KKT system in your big space, leveraging structure. And in fact, if you do augmented Lagrangian approaches, you can avoid basically all of the penalty of that big linear matrix equation, and you're back in business. But if you don't, you have a really sort of pernicious cubic scaling in all those optimization variables, which with all the sparsity and all the tricks you might leverage, still can be pretty killer. So it's important to kind of recognize this version. Like there's a really nice quantum package in that's called like dynamics. So Piccolo does the direct optimization and all the clever things so that you don't have to worry about that. But like you can do this in quantum. People have worked really hard to do it. Alice and Bob, who does like cat qubits, they have a nice package that's super cool for solving these kinds of problems. They do exactly this. Let's do it just to see that it works. We need to go backwards. So that's what this is. The adjoint equation. Backwards. Plus the like delta. And then I don't really want to get too bogged down in stuff, but we do need to line search. Because for here, well, we're not safely in like because we're trying to take control steps and we're doing this approach. We don't have the like nice QP structure that we're leveraging that makes everything safe. So we do need a line search. So you can see that's exactly what we had before. It's just this Armijo condition again. And it's basically the current cost. And then you're just checking like the directional derivative and the constant that we talked about that like weakly does that line. Same game, we'll backtrack and we'll just kind of like make sure that we don't break our steps. So that's what we're doing here. And we'll return the backtracking factor just so we can kind of keep tabs on it. Here's some parameters just for kicks. I don't know, whatever. Okay, so how's it look? So we have an initial trajectory because we have to start our problem locally. And then what do? Is we fill in all the other containers for the variables we care about, which are like u, x, and then the change in u, which will give us like, you know, the step we're going to take. And then the Lagrange multipliers for the backward. And then this is for the line search, because we've got to deal with checking if we've overstepped on our controls. So let's just look at the loop. So while the steps are still basically big, and we're not below the tolerance of like, you know, we're close to a minimum, keep going, and we haven't exceeded max iterations. Go backward using what we know already from our initial guess to get the Lagrange multipliers. And then we basically compute the stuff we need, which is the step and the gradient. And like this piece gives us kind of the line search derivative we need. So then we check basically if that was like a good step. So we just go through, we get the gradient, which just comes from like the condition up at the front. If we look like, remember this was DL du. So if I scroll up, I'm so sorry. We have that. It's right here. That's all we're doing. We just need this. So if we have that gradient, and then we have our control correction, then great. We can take a step, and then we can go forward. And then we'll print some stuff, and then we'll go backward again. And then we'll go forward, and then we'll go backward, and then we'll go forward until we converge, hopefully. So let's check it out. Solver set up with all the same stuff as before, and then we'll see how we do. So not too bad. We also kind of stopped early with iterations, but like, okay, we're in the ballpark. How's it look? About the same as before. Okay.
I've asked this a long time
Yeah,
ago.
no, you're so good.
What's up with the little swinging? Like, where's that coming from?
Oh, the fact that we like kind of
Yeah.
swing around here and take this path.
Yeah.
That's exactly the earlier question. Just sort of like how we like futzed in the Q's and the R's. It's just like the optimized like trade-off between how hard you push and when creates that swinging. So like you were going in one direction. Like if we look at this, like, right, okay, so let's kind of unpack it and talk about it. So like here, what this says is like you're going left and you started left of the origin, which means I have to push right, which means that like what's going to happen is I have to push so that my velocity goes positive at some point. So I'm slowing it down, slowing it down, slowing it down, turning around. And then I'm pushing, pushing, pushing. My velocity is then going positive and increasing. And then I've got to stop because like as I'm going back to the origin, I've got to slow down so that I don't scream past the origin. So kind of the picture, I guess, we've got our line is like hockey puck was here, sliding along on the ice, going this way. We push to send it back. And then we've got to stop it right on the dime at the origin. So we've got to slow it down, slow it down, slow it down, and oops. Okay. So we kind of overshoot, which is this extra little bit. So we have like an extra oscillation. So that's basically us being like, oops, and then fixing it.
I was wondering, would the optimal solution be just hitting it precisely, slowing down and getting there with zero speed on the first try?
If
What's preventing us to getting on that solution?
our goofy choices for Q, so that it had a little fun wiggle and wasn't boring to look at. But let's change it. Where did I make Q? I can just change it down there, and then that's actually totally fine. Let's do that. Where are we here? Yeah. Okay, let's make it twice as big early and just see what happens. Maybe I need more iterations. Let's do the QP one because it's like way better.
Block as well. Jupiter isn't interactive. Reactive, I think.
Where's my? Oh, that's also, yeah, you're totally right. That was what I was getting from that. So maybe that's the way to do it because then I have to like make these again. I don't want to do that. Yeah, let's go back to the Pontryagin because we have like direct access to the Q's, and then let's actually just replot it. That's a dude. Okay, so let's make the shape different here. Let's go 10 times Q and or yeah, and let's just like try to get there way earlier. Okay, so more aggressive. Let's see. I don't actually know off the top of my head. I have to think. Let's just like futz with stuff and see how it changes. Okay, we didn't get there yet, so we didn't have enough iterations. But you can see we had to go slower because like the forcing, we weren't allowed to go fast. So let's like let it go really fast and hopefully we don't break it. Oh, we broke it. So you can see kind of unstable. Okay, so we were able to go pretty quick. What I want to do here is I want this to be like really large, but I'm using the LQR problem, which like is a futzed, like, you know, to show you guys all this stuff. And I don't know how stable it actually is because like, yeah, it's very much not. So for like good problems, we're pretty okay. I think otherwise we need a lot more iterations. So if I go up to like one of the more early problems, like the one where I'm just directly solving for controls, so I don't have to reconstruct stuff, I bet you we can change the solution shape without like, yeah. There we go. Okay, so that's quick. And then like the iterations are hidden and automated by Optum, so we don't have to like, so here you can see it goes way faster. And we just basically rip right. We don't have that extra wiggle. So whoever asked that question earlier, we definitely should have come back and like done that. That's like a good note, is like the shape of the solution and what optimum means is whatever you write down, which is the thing I was saying earlier about like when you exploit, like if you leave the solver room to exploit numerics, it will. So it's like a very important kind of design thing is like, for example, when you're doing quantum, if you approximate your system as a qubit, but it's not, and then you like tell the solver, go as fast as you freaking can, just like rip and drive the system really good to get a gate. It's definitely not going to work if that system was actually a transmon with a bunch of higher levels that could potentially be excited during the drive also. So making sure that you know what your limitations are is also sort of an important constraint. So if you have like bounds in your model that are like, hey, I'm not supposed to like drive faster than this, or I need more detail in my model because I know I'm going to worry about leakage. That needs to go in the solver or it's going to cheat. To that point, I have one more example. I lost it. The example is this one, which is the first like nonlinear optimization, which this is kind of, you can see like this gets progressively more annoying. This is why like there's software packages to like hide all of this so that you just focus on the problem setup and all the like, I need constraints. The constraints should look like this. I need objectives. The objectives should look like this. And then all of the other magic of like annoying stuff about creating that appropriate cost and gradients and Hessians, that is done for you kind of under the hood of good packages. But here's quantum dynamics, right? We talked about this. This is like rotations. Here's what I mean by that. Here's a generator for a rotation. Think like you're spinning. So you're just kind of like swinging through two coordinates. So this state now is basically just like a rotation. If you exponentiate this, you get the cosine, the minus sign, or cosine sine, minus sine, cosine, something like this. You get a rotation matrix if you put this in an exponential. So what I'm doing is I'm giving you the first example of something that's close to quantum, which is this bilinear structure, which says how fast are you spinning on that rotation axis. In quantum, you basically just, every Hamiltonian you add is a different rotation. And they don't commute and they do weird stuff, but like ultimately you're just spinning one way, like that first GIF that I showed you. You're spinning one way, you're spinning the other. You're trying to manage the fact that they don't commute, and you want to rotate. Same exact control problem actually as like a quadcopter or something, except for that quadcopter can also go forward and back. So all of this super similar. The only catch that's new is when you solve a problem that has nonlinearity, you linearize it. You approximate it locally as an LQR problem, and then you just solve that problem with all of the things we talked about, trust regions or line searches, all the care. You just do that again, and that's it. So everything we did for solve the QP, get it in one step, is the same. Solve the QP, get your Newton step, and then just be a little cautious that you went too far, and you check and do all the stuff we talked about in optimization land. Same game. So local quadratic approximations, curves, falling to that minimum, all of that same visualization, have it in your mind here. We're going to do the same thing. So here's that rotation step. We can roll it forward. We can add the objective, which is, you know, exactly what we talked about. Blah, blah, blah. I should evaluate that. Here's that local linearization. I'm making it for all the different time points because the only catch that's slightly different is it's now going to change. It's not just A the whole time. It's not just B the whole time. It's like A plus some local correction stuff because of the linearization. So you've got like a U dependence in A, depending on what that local U was. Okay. And same with B. You've got the nonlinear part where the X is from the local linearization, and then that B as a function of X acts on U. And you just locally approximate that B at whatever the current X is and hope for the best. And then these are those constraints, past step, future step. And then rather than get too locked in, here's the same thing we did before. Get those little helpers, make H, make C and D, make H and Q. Exactly what we did. Set up the QP. But now the QP is changing every step. So we'll make those little assemblers, and then here's the game. You solve the QP, return the step, and then you have to do a line search. So this is the solve the QP part that we did before. Same as always, KKT system, etc. So just collect all the stuff that you need for that, and then solve it, and then return it. And then here's the part where we iterate. Take the step, sanity check whether you're done or not, to see if the step is big, and then do the line search. All of our friends from the first section back with bigger state spaces. That's it. So it's not any different. So that's what we're going to do. We're just going to run this loop. I'm going to print stuff as it goes. It's got to locally linearize. We've got to do the line search. So if we smash enter and just see. Okay. So cost is bad. Change is big. Takes a full step confidently. And in fact, for this one, it's never scared. Just keeps taking full line search steps. Which I guess that's convenient, but not great for the narrative. So the problem is pretty well behaved. We don't have to backtrack at all. That's awesome. Okay, cool. Let's look at it. Okay, so I don't know, something weird. We can talk about this. But here's where we started. At some point, remember it was a rotation. So all we can do is we're just spinning this to try to get back to, and then I specified a goal that was the top. I guess I should have told you guys where I was going and stuff, but like we started here. Let's look at that. We started at some angle. So here's the original. Here's where we want to go. And then we just solve the QP to do that. So it just swings it around. Yeah.
Is this direct or indirect?
This is direct because it's the QP, but we're solving it sequentially. So the states and the controls are both in the big Z. We're taking a step in that big Z and a step in the Lagrange multipliers at the same time with that KKT system. And that's what we're spitting out here with the SQP step, the step here. This is solving that equality quadratic programming.
And was the last example direct or indirect?
The Pontryagin example is it's indirect in the sense that it's a forward shooting and then a backward shooting. So you never create like all of these defect constraints and enforce those as constraints. So like the structure that makes it direct is like, are you solving like a nonlinear program where like you have that structure that says like enforce the constraint, or have you eliminated the constraint via some math? So like our dynamics constraint in the Pontryagin example, we got a forward solve and a backward solve. So the difference between that and the original was we only had the forward solve and we dropped really all our KKT stuff. And the trade-off was we had this big control landscape, which could be weird and nonlinear. When we switch to the Pontryagin example, we use the KKT to get a forward and backward solve. But otherwise, the dynamics constraints are not actually a constraint. We've like we've gotten rid of them by doing the KKT system and looking and being like, oh, that's a forward ODE and a backward ODE. So it's like a tricky thing. And in fact, that Pontryagin example I've described, you can do the same thing where you can solve like an iterative LQR. So you can like locally solve the forward solve, locally solve the backward solve, update, forward solve, backward solve. And you can actually do that first or second order. So you can get a Newton step if you do that very carefully. And those are called, the first order is called iterative LQR. for obvious reasons. The second one is called differential dynamic programming. Both of those are super common in like robotics and stuff, and like doing those in a smart way to manage constraints is like, you know, kind of a game you can play. But basically, yeah, the reason you would do that is when you're like memory limited. So the trade-off is basically like you do those problems when you're like not that maybe concerned about getting a perfect answer, like if you're doing the control problem like online. Maybe you solve it, you get an optimal control, your hardware takes a few steps, and then it just solves another problem based on where it ended up. And that way it gets kind of robust. So like if it misses, it just fixes where it was. So like think like that's like model predictive control, which is like if you're like Boston Dynamics, you might carefully construct all of your dancing robot scenes. But if you're actually deploying a robot in the field, you can't like solve for that full like dance routine. You have to be like, all right, I'm gonna like have this drone like navigating a space. So it has to like figure out where it is, take a path, follow it for a bit. And then if it misses slightly because a breeze picked up, it has to reassess, keep going. And so that like online synthesis, depending on like your resource constraints, you might solve it in a algorithm like this because you're memory limited, or an algorithm like the QP because you're smart and you could do like augmented Lagrangian or something and like get really good performance. But yeah, so it's all about kind of trade-offs that these solutions have. Nice. Okay. So I said a lot of words here, but we like basically just did LQR 3 or 4 ways. 3 ways or 4 ways. I want to ask one question here, which just really quick is like, why did we miss? So I said we had to rotate, and I was trying to rotate to like 1, 0. I wanted to get to this pole. I didn't get there. Any thoughts about why? Yeah.
I have a question. So,
Dang.
is this is still a phase space plot? So your goal is to get to.
This is a lie. I didn't change my X and Y
Oh,
labels.
okay. So this
Dang.
is position.
Yeah.
Oh, okay.
Yeah.
That
Sorry.
makes a lot more sense.
Yeah. Who did this? I didn't want to write more code, and I didn't realize that I'd auto-labeled the axes. So like, yeah.
So, but it's like X and Y. It's not phase space.
Yeah. X and Y. And we're controlling, you know, we started at some angle
And
here,
since you're in the
and we're
XY
trying to
basis-
swing the clock hand up to here. Exactly right.
So this is in the XY basis. This is a nonlinear problem because you have the cosines and sines from that.
It's a nonlinear problem because the way that the control enters in the ODE is you times the speed that you rotate times the like the matrix that is the derivative of that rotation group element. So like this is where it's like you're doing like actually like this is like Lie theory stuff. So you have like a Lie algebra that generates a Lie group.
So we're working in the Lie algebra of these rotations.
Yes, that's exactly what quantum is. Like you're at the algebra. So like Hamiltonians are just like tangent directions. Think like the like incremental generator of a rotation. So like if you exponentiate the generator, you go from like the algebra to the group, which is just a way of saying you like just spin around for longer and longer times because like the solution is an exponential. That's just like the fancy way of saying that. Yeah. Okay. So that's some fancy words of basically just it's an ODE and it looked like that which had the U and the X there, which is different than the ODE for Newton's law, which was linear. That's the like key introduction is that this is the first bilinear control problem you've seen, and all quantum problems asterisks are bilinear. So you're pretty much covered if you understand how to do a rotation. Then you just need rotations in bigger spaces with more variables and more ways to rotate. And that's really it. Okay. Nice try on dodging the question. Why did we miss? So how do you go from here to here? Yeah.
Is this just like a discretization error or something?
Yeah. Yeah, exactly. So remember we said like the optimizer can only do the stuff you plugged in, and we discretize this rotation. Kind of dumb, which I kind of maybe didn't say that clearly, but like I tried to highlight it at the start. Okay, pretend you know that those are labeled correctly. Which is that when we do the, oh gosh, there's a lot of stuff. When we do the local bilinear model, we have to discretize this thing. And remember, like, choice of discretization and accuracy of that ODE and that constraint, you know, informs like how well you can actually satisfy. And so like what's happening is like when you do a forward Euler, which is what we did, you can like overshoot. If we did like a different kind of discretization, we might have undershot. And it's actually only if we like perfectly preserve the energy or that constraint with our ODE integration that we would have stayed on the curve. That's my punchline about quantum. If you're not smart about the ODE, you might lose that norm preservation that you care about, which is that the state has to stay one in norm. Yeah.
Could we just renormalize the state at each time step? Like if we're doing a forward ODE solve, could we divide out its norm in between each of these little steps to kind of cancel out the...
You could try. Yeah. That would be kind of kludgy, I think. And you might be able to get somewhere close to it, but it's better to just like basically have the ODE handle that, or to take smaller time steps, or just kind of like, yeah, fix it in post is really like the right answer. Yeah, like you really do just have to kind of figure out what, either I know that I did it wrong, but I got close and I polish, or, you know, I just do it right from the jump. And I'd recommend just doing it right from the jump. But that's fair. Because like, you know, you kind of just need something with like the right numerical accuracy to fix this problem is really the punchline. Yeah.
Right. To add to that, this isn't a normalization issue as much as a grid size issue, is it? Like the discretization prevents you from getting to a state which is normalized at that point, right? It's not like renormalizing would fix it, because we still haven't fixed the discretization problem.
But if you sort of just like evolve and plop back onto the manifold that you're on, that's actually like a kind of a fine trick sometimes.
I see.
And in fact, I think that also is like maybe a tensor networking thing. Just
Sorry,
like,
what?
oh, like a tensor, like I think like having like a high dimensional space, having an approximation, following like the like approximation and like pushing yourself back onto the manifold and then keeping going, but like just gluing yourself down. Is that right?
No.
Yeah, look at that. Woo! Okay, so synergy. Look, there we go. Yeah, so that trick totally would work here, but it's better to just encode it. Yeah. And then I don't know what happened here. This is like a game where like choosing good control spaces is key. And this is where I'll talk about like the quantum control stuff too. Yeah.
So, so some time ago that there are some Verlet algorithms that allows you to preserve energy in the kind of simulation.
Like storm Verlet integration. Yeah.
Can we do something like that here in order to avoid these loss of traces?
Yes. And you can do that. You can do clever things with like how you do the matrix exponential integration. There's a lot of ways to be clever. Or you could just be like kind of lazy and just be like, SciML, everything is like differentiable, and I can just like solve the ODE with like a high tolerance. And yeah, it has a bunch of layers. But if I know that like I'm not taking a huge step, because like in direct optimization, I have these knots and that's as far as I have to go. I don't have to evolve the full dynamics all the way. You can just even like get those gradients from that tiny little step, and you don't have to get like the huge gradient from like a giant ODE integration. And that's like why numerically they're a lot more stable, because you don't evolve very far. So if you can do it very accurately with those steps, then yeah, just like you have a nonlinear function, which is like solve the flow map or solve the ODE forward, pick your favorite one, get a good tolerance, and then just like find out which one is like the easiest to get a good gradient for and use that one. But yeah, there's a lot of choices. you could spend a lot of time, and you will, I think, actually. I think Michael's got you. Don't worry. I think you're going to talk how to do the integration. So more to come. Okay. I don't have a lot of time. I'm going to show you a few pictures because we never got to quantum. And we're going to get to quantum. Check it out. Okay. Oh no, this one hasn't been run yet, so we're going to do it live. Here's a quantum system. We're going to add a little drifting Z term to the Hamiltonian. We're going to control on X and Y. X and Y are just Pauli matrices. So they are, check it out, generators of rotations. 1, 1. Just like what we saw before, right? Y is just a different one with different values. It goes in a different direction. Just another rotation. And then we're going to get a pulse for some duration for this system. And we're going to set up the problem using that pulse. So it's going to go for 12 nanoseconds. And the controls are like 100 megahertz. These are just units. All we're saying is that it rotates. And your sort of game is like reminding yourself that like, if I have a matrix exponential, it's spinning around. Control amplitude and time sort of become unitless and they trade off with each other. And you're just trying to complete rotations. So remind yourself that you just kind of always have to track e to the I 2 pi is like a good way to understand that's completing a rotation. And that's kind of the time scales of your problem. It's just how big the controls are allowed to get. Controls how fast you can go. Okay. Let's look at this pulse. Oh no. I'm gonna wait for that to pop up. It's gonna get another window. There it is. Okay, this is just like some initial nonsense. Ignore this. But I needed it to pop up. We're gonna do we're gonna start in the ground state. We're gonna go to the excited state. So we're just gonna store our trajectory, which is the Z, with the controls and the system. We handle all of this for you. In Piccolo, it's like basically just to manage that. This is like storing the ODE of the problem. And then we're going to discretize it however we're going to discretize it for the optimizer. So here's a ket. We're going to create a number of knots. So this is like 100 knots. We don't want that. There's 20 knots. And then I'll talk about this in a second. We're going to set up a control problem. Solve it. Okay, so what got printed out here is just the whole problem structure. So let's peep this. Oh, I didn't. Get out of here. Okay, so some things. System size, number of knot points, and then sort of the internal state of the system. Real values, that's key. Time steps are in here, controls, and also control velocity and control acceleration. Don't worry about this. This is just inside the solver. You don't care. This is like tricks to make it look better. We'll talk about it, but like not that important. What's important is there are objectives. There are regularizers. Those things you know about. They have values. Then there are integrators that glue things together. Time step to time step. You know that now, right? Like integrators glue stuff together. At convergence, they'd be satisfied. But if you just randomly start, they're not. I have a lot of stuff going pretty well. So you've got a problem and you've got some cost, which is make fidelity good. We can solve the problem for a while. Okay, I don't know why I'm still looking at this. We'll plot something in a second. Okay, objective is terrible, right? We don't have a good fidelity solution. This is 100, like a Q in front of fidelity, which is just like a norm on how close you got to the goal of like 100 times that norm. So when this is like 86, that just means that like your infidelity is like pretty terrible. You've got like a 20% fidelity. The primal is how good the constraints are. The dual is how big the Lagrange multipliers are. So we're going to start trying to make the constraints work, which is the dynamics. So when you start, dynamics weren't really working. As you go, dynamics get better because you dial up that normal force. This number gets bigger. And then you start to make the objective go down too. So you can start to maybe relax some of this. And you know, great, we're clamping the constraints down. Life's good. This actually, Oh well. For reasons, the parameters I'm using for this solve are a little more explorational. So this dual is not just like tanking and getting smaller. It's like exploring a lot to try to get a better solution. So like whatever. But you can see like we dropped to regimes where we could be done. All right. So let's just look at the answer. Whoa, hey now. Okay. So here's the zero order hold. Here's that state flip. You started with the ground state. You turn that off. You turn this on. This looks smoother than that other rotation because basically what we've got is a velocity and an acceleration, those du and ddu terms that were in there for the controls. We're just adding regularization to smooth things up. Just a trick. It's a lot of just tricks at some point because you already know all the basics. So you could kind of like start to solve these and set these things up. But like getting them finessed is the whole point of like smooth pulse problem. It's just a hacky way to say, start with that ODE. We'll handle all the construction to make it do the right thing. Nice. Okay.
I have a quick question.
Yeah.
Can you scroll up to like the output? In this like long output, there was one of the titles here. What's the third column? Fourth column?
Objective, primal, dual.
So one of these is like effectively like the error of this.
Yeah, this is the how good you're doing at the like cost, how good you're doing at turning the constraints, the F, and how good you're doing at the lambda. Asterisks, caveats.
So if you take the PR and DU, I mean, maybe this is related to what you were talking about in terms of like algorithm optimization, but do people take this, which kind of looks like a hysteresis, right? Like it's overshooting, it's undershooting.
Yeah.
Do they take this and like smooth this and then just put that as like at the end of your general function here as a correction factor and just say, hey, like we don't even want to iterate. We know generally it's going to do this. It's going to go, I mean, for a given shape, for a given Q. Do you know what I'm saying?
Yeah.
Like
So
classify the type of, way it optimizes. Like, is there?
yeah, so there's a lot of parameters in the docs that you could futz with to change the structure of what's essentially all the line searching that you guys learned about and all the like management of the Lagrange multiplier for inequality constraints. Because inequality, you like have to turn it off, turn it on, deal with like the barriers that we've been talking about. So that process is what's really under the hood here. Is there's like line search steps and different parameters in the problem and like the size of the step and things like this and like conditioning stuff. And all of this is basically stuff that's happening under the hood to make the solve go well.
So I guess taking it out of a numerical space into like a pure like functional form, type energy.
Yeah. So
for like faster, like, you know what I mean?
Yeah, so like, yeah, there are always going to be hyperparameters because it's nonlinear and there's no way to like guarantee that like you sort of are going to converge. What this does is it makes sure that like once you have good constraints, you like maintain the constraints. So that like once you're kind of in the bowl where all the constraints are kind of getting happy, it like makes sure that you don't like wander off into like a zone that's not allowed again. So you like stay in the landscape and you can kind of like break constraints and turn them back on, but you like stay close once you get to like a feasible region. So this is like solving a feasibility problem first and then just like staying there. But that's like a lot of stuff about like how this works. The key feature is that like actually the other ways to solve this are very messy for good performance, which is why like this was such an innovation. And like the name sort of encourages the fact that like you're trying to stay in the interior of the constraints. So once you're in there and like you're feasible, you manage your Lagrange multipliers via like what's called like log barriers. Think like the log of constraints, so they blow up as soon as you get close to them. So they like have a scary wall, and you just make sure that you have all the line searches to stay in that zone. And that like process of doing that with all the right line searches so that it works is like non-trivial and why this is kind of like an innovation. You can do a similar thing where you just solve two problems. You solve an inner loop and an outer loop to manage the Lagrange multiplier in the states. And if you get that right, you get a big win over this because this has like a KKT solve in it. And this one doesn't have to do like an explicit matrix solve. It just has two gradients for the like two terms. So yeah, call back to earlier about like, I guess, how to do this KKT system, which is gradients. You're over in this space. Also, we were talking about. Yeah. So I guess I just am gonna like show another picture, which is like you can change how you represent your pulse. So zero order hold would be like matrix exponential between each time step. A spline would be like if the control changes over time, you have to solve an ODE. So it's like a different kind of defect constraint or constraint between each knot point. But you can do it and you can solve it and it'll look different. And then you can animate it. So we'll let that do its thing. And you can see now it's like a linear spline. So fun. Another thing you can do is like IP ops, great. We love it. It's been around for ages. Some people wrote a pure Julia solver. So you can do that too. And solve the same quantum control problem. Printout looks slightly different, but you get a solution in the same way. You could plot it again. And in fact, we just resolved this, so it'll just look like a more polished version of what we just did. So we do this again, same thing. Didn't really change. But like Mad NLP, fun, but it's just changing what's under the hood. Okay, this is like maybe overkill. Let's just go to the punchline here, which is actually in the talk. Yeah. Oh, shoot.
Figures.
Okay. So this is the problem I was about to solve there. I'm just going to show it to you here. So here's with cubic splines. Here's fidelity, control versus time. What I'm going to do is solve the problem with like the smooth pulse problem type structure first. I'm going to get a good solution. And then I'm going to switch and I'm going to change the objective from get fidelity to minimize time. So I guess like on the board here, like the first problem is like 1 minus fidelity, control at time, being close to this goal in absolute value. This would be the first cost. The second problem I'm going to solve is sum of all of the time steps at the different points. I'll get out of the way in a second. Subject 2. Fidelity. I think I do like 2 nines. I don't know. 3, maybe you'll see. It's some number of 9s. So you know how to solve this problem just as well as this problem. So this is just adding a constraint. There's like the dynamics are down here too. Dynamics, control bounds, etc. Okay, so getting out of the way just to point at it for a second. I know it's kind of awkward on the sidewall. 2 problems. I'm going to start with this one, solve it, pause, and then I'm going to hand it off to this one. Where I'm starting, just starting the optimization variables. And now it's different. This is on a constraint. Don't break this. But the only thing I actually care about is making it go fast. And we'll see what happens. Also, the system that I have, I did a dumb thing. I just said that like basically halfway through the Z term is spinning one way, halfway through it switches, just so that it doesn't look boring. So you'll just see like the optimal solution should be bang bang, where you like work with the rotation going one direction, and then you switch and you work with it when it flips. So that's what we're gonna see here, hopefully. First thing, it just rips right there, solution, done. Okay, but like a solution is fine, but you don't really want a solution when you're solving an optimization problem. You kind of want some notion of the solution. And in quantum, you have decoherence. You have like a sort of similar to like a radioisotope has a T1, right? You have a T1, which is that like the excited state can plop down randomly to the ground state. And you have a T2, which is that the coherence, or sort of like the phase information between 0 and 1, can also collapse. So you want to go fast to avoid these random processes killing your qubit. So that's why time is so important. So we're going to leverage that here. Watch the fidelity and watch the time. Okay, so the point is it switches because of what I said earlier. You change the objective, you can get the right solution. If you try to do this by just like adding penalties, like, you know, don't let fidelity break, keep time low, it can be very hard to manage that process. So that's a punchline. You can do a bunch of goofy stuff. The whole point is to like use constraints to do cool stuff. I have other comments on this, but yeah.
What did we say about the fidelity? Because it was all about the same. It's like pretty close. I mean, I don't know.
Yeah. Oh,
so what do we say about the fidelity relative to like, you know, what's like in this time frame?
Fidelity just needs, so the point is you put a wall up after you get in the bowl of good fidelity, and you put a wall up that says don't leave, stay in the nice bubble. So you're like in some landscape. I guess the picture would be like you have an optimization landscape, which is some space. You started over here. Maybe this is like all, you know, good fidelities. So you just sort of like land in here. And then maybe like in this landscape of good fidelity, these are like big, long time. And this down here is like time getting shorter or something. This is a crazy picture. It's not what it would look like, but like you want to go here. So let's pretend like you would have to take this path. Maybe you can kind of go like this. But the point is like you don't want to just like wander way out here and like get lost because you're going downhill. The fidelity constraint sort of keeps you honest. And so that's kind of the idea. It's initial. So the first goal, and then maybe this is the second goal. And like, who knows how accurate this story is, but like, that's like the picture anyway of like what's going on. Yeah.
What was the settings in this case? Because you are still able to get like full 100% fidelity, right?
Yeah.
So what is the solution doing? Is it that was there no noise? Was there some noise that you were able to avoid?
No noise in the sense that I didn't add T1 and T2.
Okay.
So I just wanted
okay.
to go. Yeah, the dumb, this was just Hamiltonians. It was like a closed system, so it wasn't open.
Okay.
And it was
So
just
that's why you were able to get to.
Yeah, exactly. Yeah, so in practice, like if you have a T1, you are limited, and so you like have to trade off like going faster and stuff. Yeah, exactly. But yeah, so that is in this notebook also, which will appear hopefully at some point for you guys, but for right now, that's fine. It's the same exact video, but different. Here's like another version of it. I think this one I did linear splines. This is the one that's in the notebook. Same idea. Yeah.
So how would this method change if you were on
You just change the ODE. It's in here too. Yeah, you can do an open system. Yeah, it's all in here. So like open systems, no problem. Closed systems, no problem. If you want to solve for kets, if you want to solve for unitaries, if you want to solve for processes, it just changes the ODE.
Yeah, would you be changing your ODE for like a master equation?
Yeah, you could do a master equation. Yeah, exactly. And like it just changes the structure of the problem. You have to maybe balance different costs, like sparsity will look differently, and you just want to do everything smart. So that the whole point is like, you know, you just want to use it. You maybe don't want to get bogged down in like how it works or what the internal solver is, and hopefully you now understand like what is going on. And then also like if you got really bored in the like middle part when I was like scrolling through all those solver exercises, you're like, okay, that's why like I don't want to do this. I just want to solve a problem really quick. Yeah, that's kind of the idea. Yeah. Nice. Okay, guys, I feel like we are now 4 minutes over. So I think we should probably call it here. That's basically everything. You now know how to do optimal control and quantum control. So great. Appreciate everybody's attention and engagement with all my like questions and stuff. That was nice. Thanks.